Generative AI tools, and particularly large language models, are reshaping the way professionals and businesses operate. And learning to integrate these powerful tools into your workflow effectively can significantly improve productivity, creativity, and business outcomes. You've likely seen tons of headlines promising revolutionary impacts from AI, from automation to new agentic systems. But what's real and what's just hype? More importantly, how can you practically and immediately leverage these technologies for real benefits in your own daily tasks? I'm Louis-François Bouchard, co-founder and CTO of Towards AI, and we've created our AI for Business Professionals course specifically for non-technical business professionals, knowledge workers, and managers who recognize the need to understand and incorporate generative AI, but who aren't quite sure where or how to begin. Perhaps you've briefly experimented with tools like ChatGPT or Gemini, but felt disappointed by the results. Often, that initial frustration isn't due to the tool itself, but rather a lack of clear understanding of how LLMs function, how to effectively communicate with them, and how to creatively integrate them into your daily processes. Mastering these skills requires a grasp of AI's current capabilities and limitations and continuous hands-on practice to develop genuine proficiency. And don't worry, we've got you. Adopting LLMs effectively isn't just about technical skills. It's also about cultivating an instinct to approach your daily tasks with an AI-first mindset. This means routinely asking yourself three simple questions. Can AI tools help me with this task? Which specific tools should I try? And finally, how can I verify if the tool added genuine value? Developing an intuition for when to use AI effectively not only boosts productivity, but also unlocks creativity, allowing you to spend more energy on tasks that truly matter rather than mundane, repetitive chores. This course aims to help unlock this intuition via clear applied theory, real-world insights, and tips from our team of experts, and many practical examples of successful LLM use cases for different tasks. But first, let's take a step back to late 2022. OpenAI's ChatGPT exploded onto the scene, making generative AI the biggest tech phenomenon in recent memory. It hit 1 million users in just 5 days, faster than any product before it. And today, more than 400 million people use it every week. This is now about 7% of global internet users. This AI wave hasn't just changed how people work and create. It has reshaped entire industries, unlocking hundreds of billions in revenue and adding trillions to market valuations. Just look at Nvidia. Its annual AI chip sales alone are now cruising past the $100 billion mark. So far, however, much of this adoption has been initiated directly by individuals rather than businesses. This brings both opportunities and risks. Today, there's an enormous and still largely untapped opportunity for businesses to leverage generative AI for both revenue growth and cost reduction. Yet, research consistently highlights a striking disparity between managers' growing recognition of the need to adopt AI tools and actual actions being taken. Microsoft's recent Work Trend Index found that 79% of business leaders agree that their company must adopt AI to stay competitive, and 71% would prefer hiring a less experienced candidate with AI proficiency over someone more experienced but lacking those skills. Despite this clear urgency, most organizations as a whole are still lagging behind in effective AI integrations. In the same survey, 78% of AI users admitted bringing their own AI tools to work, and 52% of people who use AI at work were reluctant to admit to use it for their most important tasks. This brings significant risk to organizations. If used poorly and without proper considerations and training, AI tools can easily bring mistakes into work outputs. Even more seriously, free plans of popular chatbots like ChatGPT do not protect the privacy of user data. This means internal corporate data can leak into training data for the next generations of models. Fortunately, this is not an issue for paid plans, which have clear terms and conditions, privacy settings, and commitments to not train on your data. Anthropic's extensive analysis of over 4 million cloud interactions further illustrates the uneven distribution of AI adoption. Software-related occupations dominate AI usage, representing 37% of interactions, while professionals involving writing, media, and communication comprise roughly half of all AI-assisted tasks, reflecting AI's natural strength in cognitive skills like reading, comprehension, writing, critical thinking, and content generation. Interestingly, while 43% of AI interactions involve automated tasks such as formatting documents or generating marketing copy, much of which hopefully will later be edited by humans, the majority, 57%, involved augmentative tasks where humans iteratively refined and improved outputs from the AI. I also want to note that while coding is one of the most popular LLM use cases to date, we only cover it lightly in this course. This course is primarily aimed at industry professionals who may be non-technical and where learning to code with AI is more of an orthogonal than a complementary tool to current roles. However, if you'd like to really dive in the code and implement LLMs effectively in your applications, we have a separate course for teaching Python coding from scratch using LLMs. This also leads into our Advanced LLM Developer course option, all on the Towards AI Academy. In all these examples, we see how AI's role is mainly collaborative rather than replacement-oriented. As AI adoption grows, the advantage will shift toward people who learn to collaborate effectively and creatively with AI tools. While we acknowledge the real fears surrounding AI's impact on jobs and society rather than simply eliminating jobs, AI enhances human capabilities, and people who learn to leverage this symbiotic relationship early will flourish. So why do many people still experience disappointing outcomes when first experimenting with generative AI tools? While many test far inferior models via free plans, often the issue isn't with the LLM itself. It's that users haven't yet mastered how to clearly communicate their intentions or their own industry expertise to the model. AI tools are powerful collaborators, but they rely heavily on the clarity and precision of your instructions. They also often need a helping hand via your own deep subject experience and your own high-quality industry-specific data. Let's bridge that gap. In the course, you'll learn to articulate your goals clearly to the AI, evaluate its output critically and quantitatively, and iterate until you achieve meaningful results. At Towards AI, our mission has always been to make AI accessible, not only to individuals, but also to organizations as a whole. Over the past 6 years, we've successfully taught technical AI courses to over 500,000 learners globally. Now, we are taking this deep expertise and extending it to non-technical professionals, breaking down complex AI concepts into clear, accessible language and pairing theory with intensive practical examples that reflect real-world professional scenarios. So let's discuss the course syllabus a bit. Module 1 is about getting a grip on generative AI. Before you start using LLMs effectively, you need to understand what they are, how they work, and how this can lead to them producing errors that seem bizarrely inhuman. This module lays the foundation covering LLM capabilities, blind spots, and quirks and core methods for overcoming them. You'll explore major AI platforms like ChatGPT, Claude, and Gemini, learn key prompting techniques, and grasp key security and privacy considerations. You'll also learn how to improve AI accuracy by supplying data and context to the model. In Module 2, we get practical and demonstrate many real classes of professional tasks AI can help with. This is where theory meets action. First, you'll see how LLMs can act as adaptive personal tutors. Then, start to explore more specialized AI apps like NotebookLM that can add new functionality. You'll branch into web search AI tools like Perplexity for structured searches and explore the latest reasoning models for brainstorming, planning, and strategic thinking. We also teach using OpenAI's code interpreter for effortless data analysis and how to turn insights into visuals with cloud artifacts. We then progress beyond fast and simple chat-based tasks and into AI agents, systems that can independently execute multi-step processes and sometimes work for over 30 minutes with minimal oversight. You'll explore OpenAI Deep Research, a standout tool for professional workflows. A deep dive case study ties all of these AI capabilities together, showing how an AI-first employee could streamline every step of planning a major AI conference. As you begin to adopt AI more widely, you'll refine your ability to create robust and reusable high-quality prompts via testing and iterating, and to share them with your team through custom GPTs. We also teach methods and process for effectively checking and editing LLM outputs to reduce the time spent on this key step. In Module 3, we introduce more AI models and tools, some of which are specialized on particular tasks. For those looking to build more advanced custom AI tools without coding, we'll also introduce intuitive no-code platforms for building basic custom AI agents. Finally, we improve actionable strategies and resources for staying ahead of AI developments, ensuring you can continue to leverage AI effectively as the field evolves. Then, the modules 4 to 14 are all optional as we diverge into industry or role-specific AI use cases and examples. This module explores how generative AI is transforming fields like sales and marketing, HR, finance, education, product development, software engineering, and customer support. Even outside of your own industry, these case studies can help you develop inspiration for how AI can woven into your own professional workflows. Module 14 contains our full strategic guide to AI adoption at enterprise and is also optional and specifically for managers and leaders who may be considering bringing AI into their team or building customized AI tools. We explore the broader AI ecosystem and the various companies and tools you will interact with as you get deeper into the AI rabbit hole. But adopting AI isn't just about using cool tools. It's about making the right choices. This module explores when to build custom AI solutions versus when to adopt external tools, while breaking down core AI development techniques like prompt engineering, retrieval augmented generation or RAG, tool integration, and fine-tuning. We then pursue with governance and ethics alongside practical management skills for overseeing AI adoption. You may wonder why a structured course is needed when generative AI tools themselves seem capable of teaching you directly. While tools like ChatGPT or Gemini are incredibly helpful for on-demand assistance, they don't inherently provide the strategic guidance, structured learning pathways, or practical advice about avoiding common pitfalls. This course is precisely designed to fill that gap, giving you clear, structured directions so you know exactly how and when to use each tool for maximum impact. Ultimately, adopting an AI-first mindset means more than just understanding AI. It's about practically embedding these powerful tools directly into your workflows to achieve tangible results. So let's get started. Whether you are completely new to generative AI, a curious professional looking to enhance productivity, or a business leader aiming to integrate AI into your organization's processes and products strategically, this course will guide you through practical, actionable skills and knowledge and move beyond to achieve a real-world potential of generative AI tools in your everyday professional life. Surprisingly, many people are still under the impression that AI models are programmed and designed by humans. This was true for older, symbolic AI systems, but it's not the case for the majority of the AI systems you are using. I just wanted to clear this up, as a lack of fundamental understanding of how these models are made leads to bad usage of these models. It can lead to people both underestimating AI capability in some areas and therefore not pushing AI usage to its potential, and overestimating AI capability in other areas, which can lead to user frustration and premature rejection of these tools, or worse, to AI mistakes that slip into work outputs. Most explanations of neural networks, especially the transformer architecture that power LLMs, gets lost in a swamp of mathematical proofs, obscure training processes, complex architecture charts, and dense code. That's all well and good if your dream is to train models from scratch or invent new architectures. But if your goal is just to begin using LLMs effectively, the practical know-how matters far more than the finer details of matrix calculus. We believe that having a thorough understanding of the fundamental design of LLMs is no longer always necessary to utilize and build LLM products effectively. That said, understanding some theoretical concepts like LLM's training objective, training data, how they generate words, and understanding embeddings can make a big difference in getting the most out of them. The aim with this video is to give you the big picture so you can fit new concepts into place as you go. By the end, you won't feel like you've mastered everything, but that's okay. The key concepts will be revisited later in the course to make sure you get them. Other concepts and less relevant jargon mentioned here will just quietly exit the stage after this lesson, never to be seen again. LLMs didn't appear in a vacuum. They are part of a broader attempt to make machines do things that, until recently, only humans could do. Artificial intelligence, or AI, is the grand umbrella term for all of this. The quest to make computers recognize patterns, understand language, and make decisions. Inside that umbrella, machine learning is the field that lets computers learn from data instead of following explicit rules. Earlier AI systems, which we call expert systems, were full of hand-coded logic, a bunch of if statements stacked together defined by a domain expert to explicitly tell what to do in which case. Machine learning changed the game. We give models lots of examples, a few basic rules, and let them figure things out themselves. Within machine learning, we have neural networks, originally inspired by the human brain, which is to say, inspired by a vague cartoon of how we thought the brain works. These networks are just layers of tiny mathematical functions passing numbers around, adjusting connections until they can recognize patterns. When we stack a lot of these layers together, we get deep learning, which is where LLMs sit. Then there's reinforcement learning, a method where AI learns by trial and error, getting rewarded for good behavior and correct guesses. Reinforcement learning techniques are often now combined with deep learning to optimize the latest LLMs, allowing us to further train these language models directly thanks to human feedback rather than pre-built large datasets. Traditionally, making a machine understand language was the job of natural language processing, or NLP, a field with specialized tools for tasks like translation, sentiment analysis, and text classification. LLMs have now steamrolled through NLP, taking over almost everything from writing essays to generating code. They also expanded into new territories like image processing and audio generation. If you had asked a researcher 10 years ago whether a language model would be explaining quantum mechanics, writing poems, and generate Python script, they'd have laughed. And yet, here we are. Now, let's get to the crux of LLMs. At their core, LLMs are sophisticated artificial neural networks. It's not magic, not conscious, and not yet plotting world domination. It's just a very sophisticated and complex function that predicts the next word in a sequence. The human brain has a vast network of interconnected neurons that communicate through electrical and chemical signals across synapses. Similarly, artificial neural networks comprise a network of nodes or neurons performing simple mathematical operations and are connected by parameters, weights, and biases, which are numbers stored in matrices. These parameters are the elements that are adjusted and learned during the model training. If this feels like a lot of information at once, don't worry, by the end of this course, words like parameters and weights will all become a part of your casual conversations, whereas some others are not that relevant. Think of an artificial neural network as a huge system of mini-computers organized in a grid, all connected, adjusting and refining numbers as data flows through. In artificial neural networks, parameters are stored in matrices and the nodes are organized into layers. Storing model parameters in matrices allows certain calculations to be made in parallel. Here, when I talk about calculations, it mostly refers to matrix multiplications. Each layer processes information by doing those multiplications and passes it to the next layer, refining raw data into meaningful output through a series of transformations. Just like a basic function like this one refines any x value into a meaningful y value. Each connection between nodes has a weight. Weights are each number inside these matrices that determines how much influence one part of the network has on another. During training, these weights are tweaked millions or billions of times until the model gets very, very good at predicting text. The deep in deep learning just means they have many layers, not that they have profound thoughts. The key to LLM's power lies in their transformer architecture, which lets them process vast amounts of text efficiently in parallel. And this transformer architecture is very data hungry. So for such a thing to start making eerily human-like responses, it needs an absurd amount of training data, in the trillions of words. This data, text, images, conversations, and a lot of other things, is gathered from books, websites, everyday conversations, and anything else the engineers can get their hands on. These datasets add up to terabytes of information, but raw text and image data isn't useful until it's transformed into something the model can process. That's where tokenization comes in. The model doesn't read words, it reads tokens, units of text that might be words, part of words, or even whole phrases. The process begins with the transformation of raw text or data into tokens using a tokenizer. Tokens are the smallest units of data that the model can work with. In the case of images or audio, tokens could be portions of those files breaking down layer inputs into manageable pieces. For example, the sentence, "the cat sat on the mat," might be split into the following tokens. Tokens are not always single words or whole words. They can be just parts of words or multiple words. These tokens are decided based on your training data and try to represent its word distribution as efficiently as possible, grouping frequently occurring characters together. Once the text is tokenized, the next step is to feed these tokens into the neural network in a way that it can process. Since the model works with numbers, tokens need to be converted into numerical representations that capture the meaning and relationships between them. This is where vectors and what we call embeddings come into play. A vector is simply a list of numbers that represent a token in a multidimensional space, and so is the embedding. It's the same thing. These embeddings are essential for capturing the relationships between different tokens. The model doesn't just need to know that a token represents the word cat. It needs to know how cat relates to other words like dog or kitten. While it's hard to visualize a space with thousands of dimensions, you can think of it as a complex coordinate system where each token is positioned somewhere in this multidimensional space. Here we see 3 dimensions, but it's the same concept if you have thousands of them. The key idea is that the position of each token's embedding relative to others indicates how similar or related they are in meaning. For example, cat and kitten are close together, while cat and garden are far apart. But kitten and puppy might be closer than kitten and dog because they both mean baby animal. The term embedding instead of vector is used because the model creates a representation of each token that embeds it in a specific place in the multidimensional space. These embeddings are learned by the model during training. Now that we have our text into something the neural network can understand, we can finally feed it and start generating new words. LLMs wouldn't be possible without transformers, a specific type of neural network architecture that revolutionized machine learning in 2017. Their secret weapon is, for the most part, the attention mechanism, which lets models focus on the most relevant words in a sentence. The details of the architecture are not generally important when getting started with using and interacting with LLMs, so I won't explain them in detail. However, it does help to understand the basics of the attention mechanism, which was one of the key innovations in this architecture. Consider a sentence, "He sat on the bank and watched the river flow." If we analyze one word at a time, the word bank could mean a place where money is stored or the edge of a river. The attention mechanism in transformers works by examining all the words in the sentence at once, weighting their relationships to one another. In this case, tokens like river and flow naturally draw more weight, guiding the model to interpret bank as the river bank rather than a financial institution. This process, where every token's influence is dynamically evaluated, enables the model to focus on the most contextually relevant information and resolve ambiguity effectively. By capturing these contextual relationships and long-range dependencies, attention layers understand the nuances of language and process it in a way that preserves meaning across a sequence of tokens. A key breakthrough of the attention mechanism is that it allowed all input tokens, say 500 words, to be processed within a single matrix in parallel in each layer, dramatically reducing the computational cost of training large models and making them well-suited to GPUs. This paved the way for much larger models with even more training data and capability as we see today. There are further innovations in most of the latest LLMs such as Mixture of Experts or the MOE architecture. MOE improves the cost and speed of operating and running production LLMs, a process called inference. In an MOE model, different layers contain multiple experts submodels, These experts are subsets of the model's nodes and parameters. This allows the model to scale effectively by activating only a subset of experts and consequently a subset of nodes and parameters, reducing the number of calculations that need to be performed to run the model. Only a part of its mini-computers are switched on, and so it requires less computation to operate. MOEs can leverage specialized knowledge within each expert, enabling the model to handle a diverse range of tasks more efficiently than a monolithic. Surprisingly, many people are still under the impression that AI models are programmed and designed by humans. This was true for older, symbolic AI systems, but it's not the case for the majority of the AI systems you are using. I just wanted to clear this up, as a lack of fundamental understanding of how these models are made leads to bad usage of these models. It can lead to people both underestimating AI capability in some areas and therefore not pushing AI usage to its potential, and overestimating AI capability in other areas, which can lead to user frustration and premature rejection of these tools, or worse, to AI mistakes that slip into work outputs. Most explanations of neural networks, especially the transformer architecture that power LLMs, gets lost in a swamp of mathematical proofs, obscure training processes, complex architecture charts, and dense code. That's all well and good if your dream is to train models from scratch or invent new architectures. But if your goal is just to begin using LLMs effectively, the practical know-how matters far more than the finer details of matrix calculus. We believe that having a thorough understanding of the fundamental design of LLMs is no longer always necessary to utilize and build LLM products effectively. That said, understanding some theoretical concepts like LLM's training objective, training data, how they generate words, and understanding embeddings can make a big difference in getting the most out of them. The aim with this video is to give you the big picture so you can fit new concepts into place as you go. By the end, you won't feel like you've mastered everything, but that's okay. The key concepts will be revisited later in the course to make sure you get them. Other concepts and less relevant jargon mentioned here will just quietly exit the stage after this lesson, never to be seen again. LLMs didn't appear in a vacuum. They are part of a broader attempt to make machines do things that, until recently, only humans could do. Artificial intelligence, or AI, is the grand umbrella term for all of this. The quest to make computers recognize patterns, understand language, and make decisions. Inside that umbrella, machine learning is the field that lets computers learn from data instead of following explicit rules. Earlier AI systems, which we call expert systems, were full of hand-coded logic. A bunch of if statements stacked together defined by a domain expert to explicitly tell what to do in which case. Machine learning changed the game. We give models lots of examples, a few basic rules, and let them figure things out themselves. Within machine learning, we have neural networks, originally inspired by the human brain, which is to say, inspired by a vague cartoon of how we thought the brain works. These networks are just layers of tiny mathematical functions passing numbers around, adjusting connections until they can recognize patterns. When we stack a lot of these layers together, we get deep learning, which is where LLMs sit. Then there's reinforcement learning, a method where AI learns by trial and error, getting rewarded for good behavior and correct guesses. Reinforcement learning techniques are often now combined with deep learning to optimize the latest LLMs, allowing us to further train these language models directly thanks to human feedback rather than pre-built large datasets. Traditionally, making a machine understand language was the job of natural language processing, or NLP, a field with specialized tools for tasks like translation, sentiment analysis, and text classification. LLMs have now steamrolled through NLP, taking over almost everything from writing essays to generating code. They also expanded into new territories like image processing and audio generation. If you had asked a researcher 10 years ago whether a language model would be explaining quantum mechanics, writing poems, and generate Python script, they'd have laughed. And yet, here we are. Now, let's get to the crux of LLMs. At their core, LLMs are sophisticated artificial neural networks. It's not magic, not conscious, and not yet plotting world domination. It's just a very sophisticated and complex function that predicts the next word in a sequence. The human brain has a vast network of interconnected neurons that communicate through electrical and chemical signals across synapses. Similarly, artificial neural networks comprise a network of nodes or neurons performing simple mathematical operations and are connected by parameters, weights, and biases, which are numbers stored in matrices. These parameters are the elements that are adjusted and learned during the model training. If this feels like a lot of information at once, don't worry, by the end of this course, words like parameters and weights will all become a part of your casual conversations, whereas some others are not that relevant. Think of an artificial neural network as a huge system of mini-computers organized in a grid, all connected, adjusting and refining numbers as data flows through. In artificial neural networks, parameters are stored in matrices and the nodes are organized into layers. Storing model parameters in matrices allows certain calculations to be made in parallel. Here, when I talk about calculations, it mostly refers to matrix multiplications. Each layer processes information by doing those multiplications and passes it to the next layer, refining raw data into meaningful output through a series of transformations. Just like a basic function like this one refines any x value into a meaningful y value. Each connection between nodes has a weight. Weights are each number inside these matrices that determines how much influence one part of the network has on another. During training, these weights are tweaked millions or billions of times until the model gets very good at predicting text. The deep in deep learning just means they have many layers, not that they have profound thoughts. The key to LLM's power lies in their transformer architecture, which lets them process vast amounts of text efficiently in parallel. And this transformer architecture is very data hungry. So for such a thing to start making eerily human-like responses, it needs an absurd amount of training data, in the trillions of words. This data, text, images, conversations, and a lot of other things, is gathered from books, websites, everyday conversations, and anything else the engineers can get their hands on. These datasets add up to terabytes of information, but raw text and image data isn't useful until it's transformed into something the model can process. That's where tokenization comes in. The model doesn't read words, it reads tokens, units of text that might be words, part of words, or even whole phrases. The process begins with the transformation of raw text or data into tokens using a tokenizer. Tokens are the smallest units of data that the model can work with. In the case of images or audio, tokens could be portions of those files breaking down layer inputs into manageable pieces. For example, the sentence, "the cat sat on the mat," might be split into the following tokens. Tokens are not always single words or whole words. They can be just parts of words or multiple words. These tokens are decided based on your training data and try to represent its word distribution as efficiently as possible, grouping frequently occurring characters together. Once the text is tokenized, the next step is to feed these tokens into the neural network in a way that it can process. Since the model works with numbers, tokens need to be converted into numerical representations that capture the meaning and relationships between them. This is where vectors and what we call embeddings come into play. A vector is simply a list of numbers that represent a token in a multidimensional space, and so is the embedding. It's the same thing. These embeddings are essential for capturing the relationships between different tokens. The model doesn't just need to know that a token represents the word cat. It needs to know how cat relates to other words like dog or kitten. While it's hard to visualize a space with thousands of dimensions, you can think of it as a complex coordinate system where each token is positioned somewhere in this multidimensional space. Here, we see 3 dimensions, but it's the same concept if you have thousands of them. The key idea is that the position of each token's embedding relative to others indicates how similar or related they are in meaning. For example, cat and kitten are close together, while cat and garden are far apart. But kitten and puppy might be closer than kitten and dog because they both mean baby animal. The term embedding instead of vector is used because the model creates a representation of each token that embeds it in a specific place in the multidimensional space. These embeddings are learned by the model during training. Now that we have our text into something the neural network can understand, we can finally feed it and start generating new words. LLMs wouldn't be possible without transformers, a specific type of neural network architecture that revolutionized machine learning in 2017. Their secret weapon is, for the most part, the attention mechanism, which lets models focus on the most relevant words in a sentence. The details of the architecture are not generally important when getting started with using and interacting with LLMs, so I won't explain them in detail. However, it does help to understand the basics of the attention mechanism, which was one of the key innovations in this architecture. Consider a sentence, he sat on the bank and watched the river flow. If we analyze one word at a time, the word bank could mean a place where money is stored or the edge of a river. The attention mechanism in transformers works by examining all the words in the sentence at once, weighting their relationships to one another. In this case, tokens like river and flow naturally draw more weight, guiding the model to interpret bank as the river bank rather than a financial institution. This process, where every token's influence is dynamically evaluated, enables the model to focus on the most contextually relevant information and resolve ambiguity effectively. By capturing these contextual relationships and long-range dependencies, attention layers understand the nuances of language and process it in a way that preserves meaning across a sequence of tokens. A key breakthrough of the attention mechanism is that it allowed all input tokens, say 500 words, to be processed within a single matrix in parallel in each layer, dramatically reducing the computational cost of training large models and making them well-suited to GPUs. This paved the way for much larger models with even more training data and capability as we see today. There are further innovations in most of the latest LLMs such as Mixture of Experts or the MOE architecture. MOE improves the cost and speed of operating and running production LLMs, a process called inference. In an MOE model, different layers contain multiple experts submodels. These experts are subsets of the model's nodes and parameters. This allows the model to scale effectively by activating only a subset of experts and consequently a subset of nodes and parameters, reducing the number of calculations that need to be performed to run the model. Only a part of its mini-computers are switched on, and so it requires less computation to operate. MOEs can leverage specialized knowledge within each expert, enabling the model to handle a diverse range of tasks more efficiently than a monolithic or dense network that applies the same computations to all inputs. You can think of this as equivalent to a diverse team of human specialists where only the relevant experts are consulted for a specific problem. Everyone's time is not wasted in an all-hands meeting for every problem, hopefully not too often at least. Now that we've seen how these models are made, let's dive into the training part with the first step, which we call pre-training. The technological jargon from this section, softmax, backpropagation, gradient descent, and more, is unimportant for this course, but we'll go ahead and reference these famous terms anyway for context and just as fun facts. During training, the model engages in a massive game of prediction. You show it part of a sequence, sentences in the training data from web pages, books, or whatever, and it has to guess what comes next. It starts out clueless, throwing out wild guesses like a toddler babbling nonsense. But every time it gets something wrong, you slap it on the wrist, mathematically speaking, and you nod approvingly every time it gets something right. This goes on billions of times until the model gets scarily good at making predictions. Future tokens from the input sequences are masked or hidden to the model, essentially to avoid cheating in this prediction game. For example, if it sees the cat is on the, it might say mat or maybe table. Or if it's feeling adventurous, it could say roof, because cats are unpredictable after all. The key is that it doesn't just memorize sentences. It picks up on patterns. It learns that cat is more likely to be on a mat than, say, a tax return. Well, if you put your tax return on the ground, the cat might go directly sit there, but you get the point. But how does it predict the right word? The model isn't just making a wild guess. It's running the sentence through our layers of tiny interconnected mathematical functions, crunching numbers and refining probabilities at each step. Instead of saying, I'm sure the next word is math, it produces a list of options with different probabilities. At the very end, this probability soup gets sorted using a function called softmax, which helps the model decide on one answer while keeping other possibilities in mind. This is also where the temperature parameter you may have seen or experienced with happens. It modifies the softmax function to add or remove randomness in these probabilities. Now, this guessing game alone wouldn't be very useful if the model didn't learn from its mistake. That's where backpropagation comes in. If the model confidently says chainsaw instead of math, we need to correct it. Backpropagation is like rewinding the decision-making process and figuring out which parts of the network led to that ridiculous answer. The worst offending parameters, the ones that nudge the model towards chainsaw, get slightly adjusted so it's less likely to make the same mistake next time. To make sure this whole process doesn't spiral out of control, we use gradient descent, a method that helps the model adjust just the right amount, like nudging a steering wheel instead of yanking it hard left. Train too cautiously and it takes forever to learn. Train too aggressively and it overreacts, making it unstable. It's all about finding the sweet spot. And of course, there are plenty of ways things can go wrong. The model might overfit, meaning it memorizes training data too well and gets flustered when faced with new inputs, or its parameters might explode higher in successive calculations, turning into unmanageable numbers that wreck everything. In practice, training LLMs effectively requires high levels of complexity and several nuanced techniques to ensure optimal performance and address these issues. In short, training an LLM is a massive numbers game where the model plays fill-in-the-blanks over and over again, learning from its mistakes and fine-tuning itself along the way. While the model is trained on huge amounts of text data, it doesn't simply store and memorize this information. Instead, it learns to navigate and contextualize the training data, recognizing patterns and relationships that form the structure of our language and shared human knowledge. You could think of the LLM training process as compressing enough information about features, patterns, and relationships found in and between data in its training set to be able to produce a lossy replica of as much as its training data as possible. For example, LLMs may produce outputs that seem coherent but contain factual inaccuracies or hallucinations as it tries to guess at the blanks in its knowledge. This can be similar to how a lossy image file might look clear but loses pixel-level detail. Depending on the resolution, some key details of the scene may get confused. Another way to understand this training process is that it's basically simulating what you are training it on. What I mean is, if you train the LLM on the internet, you basically train it to become a kind of simulation of the internet, where if you give it a part of a Wikipedia page, it will just predict the rest of the same exact page. Predicting the next word or the next token in a sequence can require developing a surprisingly complex understanding of grammar, of the interrelationships between different parts of the text, and fields of human knowledge. For example, when training on a short crime novel, a lot of complexity is needed to accurately predict the next word in the sentence that reveals who was the murderer at the end of the story. Remember, all the useful information an LLM learns during training is stored in its model parameters. The model has to learn patterns and features in its data rather than just memorizing facts, partly because it has a very constrained memory budget. For example, even if LLMs are super large, like Meta's popular Llama 3 70B, they are trained on way more data. For example, this Llama 3 is trained on roughly 15 terabytes of data. It then forms a model weights file of just 140 gigabytes, which means the information is compressed around 100 times. These LLMs cannot memorize all their training data in their model weights, and this is not what they are designed to do. The model needs to develop a much more robust ability to understand, search for, use, and combine the features learned from its training set than you could get from simply memorizing everything in a database. And by the way, it's key to remember this when you work with LLMs. You can't assume it knows things just because they are on the internet. On some occasions, the model does in fact memorize certain facts and passages of specific text more directly. But this word-for-word memorization is generally only for super commonly repeated information in its training data. such as popular open source books or expressions that appear particularly often on the internet. This occasional full memorization can be beneficial, but it can also be an issue when using these models in practice. You may need to build safeguards to avoid generating copyrighted material or harmful expressions. AI labs normally build these safeguards into their user-facing chatbots and applications, but they are not perfect. Once the pre-processing is done, comes the post-training process. So you've got this big fancy language model. You've spent months feeding it mountains of text, letting it play its giant word guessing game, tweaking its internal dials through trial and error. Great, but here's the problem. It still doesn't know how to talk to real people properly. You are still in the internet simulation state. After the initial pre-training phase, LLMs need to undergo further refinement through what we call instruction tuning and reinforcement learning from human feedback, or RLHF, to enhance their performance and adaptability. This means we have to retrain the model again, twice. You see all that text it was trained on initially? It wasn't neatly labeled with questions and answers or clear-cut instructions. The model saw books, articles, random internet debates, but it wasn't trained to respond to things the way a human would expect it in a conversation. It was trained to predict the next word to generate that would make sense. So if you ask it something specific, it might just spit out a list of vaguely related questions rather than answering you. To fix this, we do something called instruction tuning or supervised fine-tuning. They are the same thing. Instead of feeding it raw text, we give it a carefully crafted dataset full of instructions and proper responses. Think of it as teaching the model how to actually follow instructions instead of just rambling about everything it knows. This extra tuning makes it much better at responding to commands, answering questions properly, and generally acting more like a useful assistant rather than an internet word blender. But we are not done yet. Even after instruction tuning, the model still isn't perfect. It might miss the point of certain questions, misunderstand the tone, provide dangerous information, or just go off on weird tangents. That's where reinforcement learning from human feedback comes in. Humans rank a bunch of different AI-generated responses to provide feedback for improving its responses to align with human preferences, or the specific policies of the AI lab creating it. Now, you might imagine that this means humans are correcting the model live as it generates responses, but that's not really how it works. The human feedback isn't fed directly into the model. It's used to train a separate system called a reward model, which then learns how to judge responses the way a human would. Once this reward model is trained, it's used to fine-tune and adapt the original LLM automatically. The LLM generates responses, the reward model scores them, and the LLM gradually learns to produce answers that rank higher according to the reward model, which ideally means to what humans prefer. So instead of tweaking every response manually, humans train a grader, and that grader is what actually guides the model's learning during training. Now, why not just have humans write out perfect answers every time? Well, because writing flawless responses for every possible input will take forever. It's way easier to have humans rank a few options than to have them come up with the ideal answer from scratch. So by building a reward model from human preferences, we make the LLM more useful, more aligned with what people actually want, and less likely to go completely off the rails. Of course, there are still problems. These models can absorb biases from their training data or from human feedback, make things up, or say things they shouldn't. Companies are constantly working on ways to keep them in check, adjusting how they respond to sensitive topics, filtering out misinformation, and making sure they don't accidentally encourage bad behavior. But no matter how much fine-tuning we do, LLMs are not perfect. They are just very, very good at guessing what sounds reasonable. So the takeaway? The pre-training phase makes the model smart, but the instruction tuning and RLHF make it actually usable. Without these extra steps, the model is just a giant text predictor with no sense of what humans actually want. With them, it starts acting like an AI assistant that actually feels like it understands you. Well, mostly. After a new model has finished training, its official release is often delayed many months to allow for internal and external safety testing. Further post-training may be required to fix shortcomings prior to release. And finally, the process of actually using an LLM that has finished training is called inference. In the context of LLMs, inference involves generating responses to questions or prompts by applying the learned patterns and knowledge from the training phase. Now, here's the catch. Inference has to be fast and efficient, especially when you're dealing with real-world applications. Nobody wants to wait 10 minutes for an AI-generated email reply or a chatbot response when Googling takes a few seconds. And remember, these models are gigantic, with billions of parameters, meaning every time they generate a response, they are crunching an enormous amount of numbers. If you ran them exactly the same way they were trained, they'd be painfully slow, not to mention ridiculously expensive. That's why AI labs use all sorts of clever tricks to speed things up. Some methods shrink the model down via techniques like quantization and more, making it smaller and easier to run. Others optimize how computations are done so you get the same output with fewer steps. So to recap everything, pre-training makes the model smart, post-training makes it usable, and inference optimizations are what makes it actually economically reliable. All these steps have a crucial role. Making inference fast and efficient is one of the biggest challenges in deploying the smartest LLMs in the real world. I hope you found this overview of how LLMs process language and how they transform vast amounts of data into human-like responses useful or at least interesting. Just remember, at their core, LLMs are giant statistical engines predicting the next word. They are remarkable tools, but they are still just that. Tools. Remember that. Thank you for watching. In the last video, we went through the basics of training large language models and really machine learning as a whole. If you didn't catch every detail, don't worry, you weren't supposed to. The goal wasn't to make you an AI research scientist in 20 minutes, but to give you just enough context to see where everything fits together. We touched on transformers, training objectives, and how LLMs don't learn like humans. That last part is key. These models have unique strengths and weaknesses that make them useful in some areas and unreliable in others. These weaknesses are crucial to understand, so you can know where you can use LLM tools safely and appropriately in your workflows and what techniques you can use to address these issues. LLMs are not plug-and-play geniuses. They often need extra work to be practical in real-world applications. Now, let's take a closer look at what these models actually learn, where they fail, and what we can do about it. We've seen that transformers spend their entire training cycle obsessively predicting the next token. But what precisely is being learned? Inside these models appears a complex internal representation, a high-dimensional vector space, just like the 2- or 3-dimensional graphs we saw in school, but in order of thousands. They are often called the embedding space, where tokens like kitten and puppy appear near each other, while chainsaw or fire wisely stay well away. This process, developed iteratively during billions of training cycles, creates one of LLM's standout strengths, a semantic understanding of your questions. It doesn't just retrieve matching keywords, but accesses interconnected layers of meaning, grasping context, nuance, and abstract connections. It comfortably handles complex queries, comparing and synthesizing across diverse concepts far beyond the keyword-bound reach of traditional search engines. This is all great, but the important bit is that this is not how humans think. The LLM isn't reasoning. It isn't forming opinions. It's just extremely efficient and surprisingly crunches probabilities, which also leads to some of its weaknesses. What we often see as intelligent responses materialize from a soup of statistical relationships between tokens stacked together in a way that feels like comprehension. What matters to us is how the system fails and what we can do to make it reliable. So let's understand these weaknesses or limitations a bit better. One of the biggest limitations of how neural networks are trained is that it's a one-shot deal. Train once, deploy, and then hope the world doesn't change too much. Training these models is no small feat either. It takes months of training on GPUs in data centers that cost billions of dollars to build, and once it's done, that's it. The model is frozen in time, blissfully unaware of anything that happens afterward. This setup works just fine for things that don't shift much, like detecting sentiment in text or summarizing decades-old news articles. But throw in something fast-moving, like new AI models, medical research, or current events, and suddenly the model is operating with outdated knowledge. That's why users often run into messages like this one when asking about recent events. This limitation is called the model's knowledge cutoff, which marks the last point in time when it was trained on new data. This isn't just an inconvenience. It fundamentally affects how useful the model is in fields where information moves fast. For example, just ask about the latest Super Bowl winner or the newest Mission Impossible movie, and the model might respond with something like this. To patch this gap, developers use external resources like web searches, Wikipedia pages, document databases, or structured data formats like PDFs and JSON files. More on this later in the course. Another limitation worth mentioning is that LLMs don't precisely store knowledge or obscure facts in their parameters, even if it appeared in their training data. They instead absorb broad patterns and generalities from vast amounts of data rather than explicitly memorizing every detail. So if asked about a niche medical procedure or a rarely cited historical event, the model often struggles. On top of this, a lot of key information is locked away in internal corporate data or in the expertise of professional employees. Even if this knowledge existed before the knowledge cutoff, the AI companies may have never gotten their hands on it and the model never saw it during training. So in any case, that's just to say sometimes the knowledge isn't seen by the model. Another obvious limitation with LLMs is they get things wrong. A lot. Sometimes they misinterpret a question, sometimes they confidently assert nonsense, just like our medical procedure, where the model could give something totally false. The main problem is that it doesn't know it's wrong. It doesn't have the concept of a truth, a fact, and a lie. It just knows words and statistical correlations. We call these lies hallucinations, even though it may not be the best word for it. Much of the time, this is ultimately due to factors we've just discussed on the limitations of its memorized knowledge and architecture. But most importantly, the model isn't fact-checking itself. It generates each token based purely on what statistically makes the most sense. If its training data contained errors, those errors get baked into its responses. If it has a gap in its knowledge, it won't admit it. It will just interpolate based on patterns. Yes, interpolate, not extrapolate. It cannot extrapolate to new knowledge unless you give it some examples or ways to get it first. It can only take what it has seen and make new connections between them, but can't develop some new paradigm or extrapolate from the data it has seen, just like other AI models before LLMs appeared. Anyways, sorry about this parenthesis, let's get back to this hallucination issue. The post-training process with instruction tuning and reinforcement learning from human feedback, which we also discussed, plays a role here. Models are rewarded for being helpful assistants and following instructions. This can also lead them to making up information just to please you. There are ways to reduce hallucinations, which we'll cover later in this course, but they never fully go away. That means any LLM-powered system needs safeguards, whether it's through external knowledge retrieval, human oversight, or clear disclaimers. To understand this concept better, take a look at this. When we ask what is the name of the towards AI developed largest open source model and what is its size, the GPT-4o model confidently responds that towards AI developed Grok. However, the Grok model was developed by xAI, which is a 314 billion parameters LLM called Grok 1. In fact, towards AI hasn't released any open source model yet, while xAI has already released Grok 3, so it's quite outdated there. This issue is not unique to ChatGPT or OpenAI. Similar LLMs like Claude, Llama, Gemini, and Mistral also exhibit this behavior. Another thing is that LLMs don't grasp chronology particularly well. Transformers and the attention mechanism processes information in parallel and relies heavily on positional embeddings to provide some sense of order. Yet, this is a crude substitute for a genuine understanding of time and cause and effect relationships. LLMs frequently jumble timelines or confuse event sequences, which you may have experienced already. Just try to get a good 6-month training plan for a marathon and you'll see what I mean. Another issue is LLMs can also absorb biases lurking within their training data. These biases usually originate in datasets that lack sufficient linguistic and cultural diversity or datasets steeped in historical stereotypes and outdated assumptions, such as much of the internet. If the training data persistently portrays women in subordinate roles or repeats harmful stereotypes, perhaps depicting certain ethnic groups as inherently violent or dishonest or whatever wrong it's saying, then the model, being a statistical echo chamber, naturally learns to replicate those viewpoints. For example, these are outputs from the GPT-4o mini model. The responses clearly echo traditional gender stereotypes, automatically associating occupations like engineer and construction worker with men, and nurse or social worker predominantly with women. Biases inherent can creep unnoticed into the model's outputs without intention or awareness. But biases aren't confined only to sensitive demographics like race or gender. They surface wherever the model has encountered uneven or skewed training data, be it industry norms, regional business practices, or specialized applications. In short, when biased patterns sneak into the data, they will probably pop up again, echoed by the model in whatever responses it generates. Biases are inevitable. Every human has biases, every government has biases. The goal here is to reduce the bad ones and focus on the good biases, like being nice to each other. Sometimes LLMs positively surprise us. They can generate answers that feel creative, applying knowledge in novel ways that go beyond simple memorization. If you ask one to write a pasta recipe in the style of a pirate sea shanty, it will do a great job, even though nobody fed it a dataset of pirate-themed recipes. The model is great at recognizing patterns and combining features from different data sources. But how far does that take us? Can LLMs solve completely new problems that require reasoning beyond what's in their training data? That's less clear. It's again what we call interpolation. And is this real intelligence? I don't really know, honestly. Much hangs on your personal definition of intelligence. After all, human creativity often similarly involves repurposing bits of knowledge from disparate fields. A key test is whether LLMs can generate correct answers for concepts outside the distribution of their training data. Right now, they struggle. They cannot extrapolate much like humans do. Their reasoning abilities are limited, and their ability to extrapolate is inconsistent. This is why, for now, human oversight remains essential when using LLMs in any high-stakes setting. Some of the best evidence that LLMs don't truly understand the world and can't generalize comes from their weird, counterintuitive failures. The alien form of intelligence exhibited by LLMs creates a paradox. The same model capable of smoothly articulating complex essays might fail simple tasks that elementary students nail routinely. Because their intelligence is statistical rather than genuinely reflective, subtle misunderstanding and hallucinations can sneak in. Even when an LLM appears highly intelligent, it may harbor fundamental misunderstandings that are not immediately apparent. Users easily fall into overestimating these models' raw outputs, leading to mistakes that can range from trivially obvious to dangerously subtle. Take a recent test with OpenAI's GPT-4o and o1 models. When asked how many R's are in the word strawberry, it confidently answered 2. When pressed to double-check, it corrected itself 3. That at least shows some progress. But when asked to list positions, it gave 5, 8, and 9, which is wrong. The correct positions are 3, 8, and 9. This isn't just a typo. It's evidence of a deeper issue. The model doesn't actually see words the way we do. Its tokenization system means that letter counting is not a simple task, and its statistical approach to generating responses sometimes leads to nonsensical answers. Another common logic puzzle shows similar flaws. If you say, Sally has 3 brothers, each brother has 2 sisters, how many sisters does Sally have? Initially, ChatGPT-4o claimed Sally has 2 sisters. However, when breaking down the logic, it concluded that Sally is one of the 2 sisters shared with her brothers, leaving only one sister beside her. This highlights a critical weakness despite impressive conversational abilities. LLMs often struggle with simple relational reasoning, demonstrating that even basic tasks can lead to unexpected errors. One complexity of judging LLM's ability by anecdotal examples of failures is that the inner workings of an LLM are actually very complex. It may have the capability for more complex reasoning and for finding the correct answer to these logic puzzles, but the highest probability next token chosen for the output is instead hijacked by simpler neural circuits that memorize the similar looking yet different logical puzzles in the training data. Sometimes different prompting can prime the model in different ways and unlock more careful thinking. Navigating all of these paradoxical AI failures requires vigilance and a more advanced understanding of how they work and why they have these failures. It also underscores why rigorous checks and guardrails remain critical when deploying LLMs, particularly in high-stakes scenarios. So far in this video, we've been pretty harsh on LLMs, maybe enough to have you questioning why you've bothered with a whole course about using them. The truth is, we genuinely appreciate what these models can do, despite their odd quirks and occasional faceplants. There's plenty we can do to mitigate their shortcomings and eccentricities, which we'll get into shortly. But we think it was important to first make sure their peculiarities sink in deeply and to help you conceptualize precisely where and why these issues arise. Understanding the anatomy of these failures isn't pessimism. It's a foundation for effectively deploying LLMs in ways to keep their strength front and center while limiting their weaknesses. Many techniques have been developed that considerably improve their dependability, such as careful prompting and providing context, which we will cover in the following lessons. Other advanced techniques include retrieval augmented generation, or RAG, providing relevant data to the model at scale, specialized fine-tuning, which is adapting the model parameters to improve performance on specific tasks, and integrating external tools. Many of these techniques are packaged and available directly in chatbots such as ChatGPT or other generative AI apps built on top of these same models that are customized to specific industries or use cases. Nevertheless, knowing precisely when to trust an LLM and when to double-check its output also remains crucial. The selective skepticism paired with skilled usage and the right choice of AI model or AI app can transform a flawed intelligence into an incredibly useful assistant. Some models or customized applications built on top of them are far more capable and reliable at certain tasks than alternative models. But with new state-of-the-art models and tools coming out daily, keeping on top of the best tool for your task is no easy challenge. What does this mean for you? It means opportunity. The gaps in LLM performance create a huge opportunity for those that master the model's weaknesses, pick the best AI tools, and learn to combine them with their own industry-specific knowledge and workflows. Next up, getting to know some of the leading LLMs and their consumer-facing applications. Let's get to work. Thanks for watching. Let's talk about talking to AI. Before we introduce overly complex terminologies and approaches, the rule is super simple. If you can precisely explain what you want, your chances of getting what you want increase. That's the main thing to know, and you'll get 80% of the job done. The remaining 20% varies for every task and every LLM. And that's where the techniques we will discuss now will come in handy. So here are the best tips to remember when prompting an LLM, what works well and what doesn't. Just to set a common baseline, we'll define a prompt as the input we provide to an LLM to tell it what we want. It's often phrased as a question, a task description, or a set of examples and instructions. Think of it as the interface between human intent and machine output. There's an old principle in computing: garbage in, garbage out. If you feed poorly constructed prompt, you will likely get a poor answer. Prompt engineering has now become a standalone job title in some cases, but more broadly, it's more of a new valuable skill, much like knowing how to Google or use a spreadsheet. You don't need a PhD in machine learning, just practice and use common sense. Whether building products with LLMs or using them in everyday applications, refining your prompting skills will pay off across many roles. The precise prompting techniques will change, but at the core, the skill is simply developing an intuition for using, instructing, and interacting with LLMs with natural language to get the most productive outputs and benefit from the technology. While some forms of prompt engineering are relatively brittle hacks that people have found to get desired results from the model, the broader discipline is simply effective communication with LLMs, which can be relatively similar to effective communication with humans. In particular, it often requires giving clear and concise instructions to what you can think of as a relatively novice assistant or intern, where you preemptively think through ways they may make mistakes or get off track. In practice, you cannot second-guess all of these potential mistakes. There will still be new edge cases where your prompt isn't followed. This is why prompting is an iterative process where you test and improve your prompt over time, either in the same ongoing discussion or retrying with some edits in the original prompt. Getting the best output requires evaluation of results across a wide range of potential use case scenarios. This is where patience will be your good friend. In this video, we will only provide an overview of the most popular and valuable prompting techniques, but I highly recommend checking the resource Learn Prompting, where we were early contributors to the materials for a more in-depth understanding. First of all, you may wonder, why learn how to prompt since I already know how to communicate my intent? It's simple. Because your intent and the AI's understanding of your intent is slightly different, and it makes a huge difference in how well an AI responds to you. If you know how to craft a solid prompt, you'll guide the AI to give you way better answers and save tons of time and costs. The way you phrase things, the details you include, and the structure of your request all play a role in getting the best possible response. Plus, different AI models have different quirks. Some are chatty, some are straight to the point, and some follow instructions better than others. Knowing these differences helps you tweak your prompts to get exactly what you need. At the end of the day, prompting is how you get an AI to do what you actually want. One of the simplest ways to prompt an LLM is just to ask. This is called zero-shot prompting. You don't give it any examples or extra instructions. Just throw your request at it and see what happens. LLMs have gotten pretty good at handling a lot of tasks right out of the box. If you ask it to summarize a Sometimes that's all it takes. No setup, no context, just a straight request. But other times the AI spits out nonsense, which is why there are more structured ways to prompt, like few-shot prompting. Providing a few examples of tasks and responses can make a big difference. This is called in-context learning or few-shot prompting, as I just said. By seeing some sample inputs and outputs, the AI picks up on patterns and applies them to similar tasks. This helps with both accuracy and keeping a consistent style. For example, if you want the LLM to summarize novels in a single sentence, you can give it a few examples first, like these, and then ask the AI to do the same for Frankenstein, for example. So the LLM might respond with something like this. That's way better than just saying, summarize Frankenstein, because now the AI understands the format and tone you are looking for. You are essentially teaching it how to think by example on the fly. This idea isn't new. A breakthrough paper called Language Models or Few-Shot Learners that used GPT-3 a few years ago showed how modern AI can perform all kinds of language tasks just by seeing a few examples, something that used to require massive amounts of training data for each specific task. For current LLMs, few-shot learning is common, but back then this was a game changer, and it still is a game changer. I always try this first when tackling a new task. But few-shot learning also has its limits, especially for complex tasks. That's where more advanced techniques like chain-of-thought prompting come in, helping the AI think through problems step by step. This is needed because LLMs have a habit to jump straight to the answer, sometimes skipping important reasoning steps. You don't want to directly answer a complex mathematical equation or a brain-wrecking riddle. You take time and decompose them in multiple steps. Chain-of-thought prompting encourages the model to do exactly that and slow down to explain its thinking process before giving a final answer. It's like making the model think out loud. Sometimes it's just as simple as saying, let's think step by step. And the model breaks a problem into smaller logical steps instead of rushing to a conclusion. You will see the benefit of this technique primarily for logical reasoning questions like if a farmer has 48 apples, sells 20, and divides the rest equal into 4 baskets, how many apples are in each basket? If the model tries to solve this in one go, it will probably make a mistake. But if you guide it by saying, let's think this through step by step, it will likely respond with something like 48 minus 20 leaves 28, and 28 divided by 4 is 7. With that breakdown, the final answer, 7, is much more reliable. That said, chain of thought prompting doesn't always work perfectly. Its effectiveness depends on the model and the task. It's particularly useful for arithmetic, logic, and symbolic reasoning, but doesn't always help with other types of problems. You are probably thinking that there is a limitation for every benefit. But that's a great thing because now you can directly use the technique that works for your task category, reducing the trial and error. These techniques will likely be less and less necessary as LLMs evolve, but they still help in improving results. New techniques will surface to improve results and we'll be sure to cover them on the channel and our course. Nowadays, reasoning models like OpenAI's O1 and DeepSeek's R1 do this chain of thought-like reasoning automatically with the goal of spending more tokens for more complex queries and fewer on easier ones. Just like we spend more brain power when answering a complicated question. Another technique that helps is role prompting. Sometimes AI needs a little role play to get into the right mindset. For example, if you ask you are a physics teacher, explain Newton's laws of motion in simple terms, the AI will take on the role is providing detailed, structured context upfront. Instead of going back and forth refining a vague prompt, it's much better to start with a well-thought-out brief that includes all relevant information, such as database schemas, past attempts, or specifics about how you want the response formatted. The focus for these models should be on giving it all the details it needs upfront, allowing it to generate a well-reasoned answer without extra guidance. This approach helps O1 generate complex code, structured analysis, or technical explanations in one go. While it's powerful in these areas, it's not the best choice for creative tasks like writing a haiku where traditional LLMs handle those faster and cheaper. There's also something called system prompts. They are additional and sometimes hidden instructions that shape how a model behaves throughout a conversation. Unlike user prompts, which are provided during an interaction, system prompts are set at the beginning and establish general guidelines for the model's responses. They define the model's tone, ensure consistency, enforce ethical rules, and guide how information is structured. For example, in a news summarization tool, a system prompt might instruct the model to always format its responses as a bulleted list. Similarly, OpenAI's DALL-E uses system prompts to refine image generation. If you ask for an image of an AI robot, the model will automatically expand on that request to ensure the generated image aligns with ethical standards and provides a clear, structured result. Not all system prompts are visible or editable by users. When chatting with GPT-4o through ChatGPT, the model operates under an unseen system prompt that influences its behavior, and users cannot modify it. However, when interacting with GPT-4o programmatically via an API, developers can provide their own system prompt to customize how the model responds, tailoring its behavior to specific needs or applications. All these techniques are a great starting point, but if you think using these techniques means you will get the perfect output on the first go, you will be disappointed. Coming up with the perfect prompt on the first try doesn't always happen. A lot of the time, it takes a few attempts. This is where an iterative approach comes in. You start with a prompt, see what the model gives you, tweak it, and try again. It's a back and forth process where you gradually fine-tune your request to get exactly what you need. Even experts don't get it the first time. They test, experiment, and refine. Say you ask, tell me about the French Revolution. The LLM might give you a long, detailed response when a good workflow is to draft a prompt, test it, review the output, tweak the wording, and repeat until you get what you want. Each iteration brings you closer to the ideal response. An imperfect answer isn't a failure. It's just feedback. If the LLM didn't interpret your request the way you intended, rephrase it or add more details and try again. At the end of the day, writing good prompts comes down to being clear and precise. The more specific the instructions, the better the results. If a prompt isn't working, refining it quickly is key. A good approach is to anticipate how the AI might misinterpret the request, test prompts under different conditions, and avoid making assumptions about what the model understands. Simplicity also helps. Prompts should be straightforward without unnecessary complexity. It's important to balance general cases with edge cases, thinking about how the prompt will perform in real-world scenarios. One thing that we always need to keep in mind is that LLMs sometimes make things up. The hallucinations, which happen when the model confidently spits out wrong or misleading information. The most common case is factual errors, like claiming New York is the capital of the United States. Another issue comes from the outdated training data. If you ask about the 47th President of the United States, but the model was last trained before the election, it won't have the latest information and might guess instead. Sometimes hallucinations happen because of the way we phrase a prompt. If we ask an LLM to confirm something that isn't true or feed it incomplete information, it might take that as a fact and build on it. Unfortunately, hallucinations aren't fully solvable because of how LLMs work. They generate responses based on patterns, not direct access to a real-time knowledge base. That's why it's always a good idea to double-check important information yourself, especially for anything factual or high stakes. Although now there's a fix for this, you can ask the LLM to provide sources by enabling web search where available. ChatGPT, for example, only cites sources when browsing is turned on. If the chatbot you are using doesn't have web access, it won't be able to fetch real-time references, so relying on it for citation without verification isn't the best idea. When accuracy matters, take LLM responses with a grain of salt and cross-check with trusted sources. In the end, getting good results from an LLM is an ongoing process of refinement. Clarity, context, and specificity makes all the difference. A vague prompt can lead to irrelevant or even incorrect answers, while a well-structured one gives the LLM a clear path to follow. Since such an advanced language model doesn't come with a user manual tailored to every request, your prompt acts as that manual. Think of prompt engineering as learning a new way to communicate, one that bridges human intent with machine understanding. It doesn't take technical expertise, just practice and a willingness to experiment. Also, as a final note, remember that different models respond differently. So prompt optimization isn't a one-size-fits-all. Reasoning models like O1 requires a distinct approach, while traditional LLMs benefit from more structured prompting techniques that we discussed. I hope this video was somewhat useful to you and that you better understand how prompting typically works. Thank you for watching, and I will see you in the next one. The impact of LLMs on human work is complex and varied across different job categories. Right now, we think LLMs are most likely to automate or significantly augment tasks that are routine, repetitive, and text or image recognition and interpretation based. In creative, analytical, and specialized professional services, LLMs are still more likely to assist predominantly human-led tasks rather than replace them. We also see a natural progression as we scale foundation models' capabilities and improve LLM pipelines' reliability. We progress from unreliable intern assistants that can help with some one-off tasks and data processing, but need lots of clear instructions and lots of extra time checking final results, to useful copilots, which can assist us as we work and increase our productivity, to agents that can be set to perform relatively complex tasks for hours or days at a time, but still need instructions and checking, and finally, to fully automated workflows. Some of these come earlier depending on the reliability threshold of the task and its suitability to the capability of the current LLMs. At the moment, most LLMs applications are in the first or second category, but agent-based systems are more and more popular and improve daily. This will be the biggest shift from a tool to a complete entity, but also the most complex shift to achieve. As LLM technology continues to advance, it's important for workers across all sectors to adapt and develop skills that complement AI capabilities. This includes focusing on human traits such as creativity, critical thinking, emotional intelligence, and complex problem solving. And by the way, that doesn't mean AI can't help with these skills. It certainly already can, as we will see in the course. As workers' jobs begin to change rapidly, it will be essential to invest in reskilling and upskilling programs to help workers adapt to changing job requirements, just like leveraging computers and Excel rather than paper tables. Humans will have to learn how to use AI, understand its ever-evolving strengths and weaknesses, and think through how to adapt their workflows to make use of AI capabilities. We think AI-driven job losses are likely in some sectors where AI boosts worker productivity in some workflows of products that are still supply or demand limited. However, we think it is more likely you will be replaced by somebody else who has taken time to learn how to use AI effectively than you are to be replaced by AI directly, at least in the foreseeable future. The future of work will involve a collaborative relationship between human and AI, with LLMs handling routine tasks and augmenting human capabilities in more complex areas. So here are some of our thoughts on how different categories of human work could be impacted. Knowledge work and information processing LLMs are particularly well suited for tasks involving information processing, analysis, and synthesis. Their impact in this area is likely to be substantial. LLMs can quickly process vast amounts of information, identify patterns, and generate summaries. They are likely to significantly enhance the efficiency of researchers, analysts, and journalists. And talking from my own experience, I can confirm it does provide incredible help to my research and writing, which we have practical examples later in the following videos. Writing tasks such as drafting reports, articles, and marketing copy can be incredibly aided by LLMs when leveraged in the right way. While human creativity, nuance, style, and error checking remain crucial, LLMs can assist with ideation, structuring, and generating initial drafts. We have a whole dedicated video coming on this. LLMs can handle a large portion of customer inquiries, reducing the need for human customer service representatives, especially for routine queries. Just keep in mind that it won't replace all of them, but it certainly helps with easier and safer queries. The impact of LLMs on creative tasks is likely to be more assistive. Text-to-image models can assist in generating visual concepts, but human artists will remain crucial for original artistic vision and execution. We still need a good designer eye, but AI helps do much better both for artists to scale up production or creativity and for us non-talented people to produce something that is nice to see. LLMs can now even aid in generating melodies, lyrics, or whole songs. But human musicians will still be essential for creating emotionally resonant, culturally significant, and live music. Still, if you're looking for a background song for a video or elevator, it can be a nice and cheap option. LLMs can significantly augment technical work, but are less likely to replace humans in these areas fully. For programming and software development, LLMs can assist with code generation, debugging, and documenting. Cursor or even just ChatGPT are incredible examples of this. Still, complex problem solving, system design, and ensuring code quality will require human expertise. LLMs can help with legal work, from research and contract analysis to drafting simple legal documents. However, interpreting complex laws, developing legal strategies, and representing clients in court will remain human-centric tasks. You don't want an AI to hallucinate cases or fake proofs. LLMs can easily assist with financial duties like data analysis, report generation, and risk assessment. They can help in claims processing, policy analysis, and customer interaction. Lastly, while LLMs can assist in analyzing medical data and suggesting potential diagnosis, final decision-making and patient care will still rely heavily on human medical professionals. For example, in my PhD, I was using AI to help diagnose multiple sclerosis by training an algorithm to detect early lesions in brain MRIs, which we then sent to expert radiologists to confirm the diagnosis. Nothing was fully automated, but it helps save a lot of time for radiologists to flag relevant information. A lot of processes is currently being made on humanoid robots, and in many cases are now integrating LLMs and transformer models into the architecture. Most are still a bit away from commercialization, and manufacturing capacity will also be a bottleneck to adoption when they are ready. For now, LLMs have limited direct impact on physical tasks, but they can indirectly affect these jobs. LLM can assist in process optimization, inventory management, and robotic control systems. However, many physical tasks will still require human workers because of inconsistencies or expensive sensors and hardware systems. While LLMs can optimize routes and schedules as in Google Maps, the physical act of driving and operating vehicles will require either human operators or predominantly non-LM based AI technology for self-driving cars. The main blockers here is regulation and ethical concerns, but not really the technology, though it isn't fully perfect. LLMs are less likely to replace human managers, but can assist in various ways. They can analyze data and provide insights to aid decision-making processes. They can help in task allocation, scheduling, and progress tracking. They can assist in analyzing employee performance, data, and suggesting improvements. They can automate and help streamline many of these tasks. Moreover, a great manager can now do much more than they used to be able to do by leveraging LLMs as another type of employee they are managing. Giving clear directions and goals, one can leverage a powerful model like GPT-01 to do some quite complex tasks almost on its own. LLMs have significant potential to augment educational processes. They can provide tailored explanations and practice exercises for students. They can assist educators in developing course materials and assessments. They can provide 24/7 personalized tutoring support, remembering past conversations and learning styles. Although human teachers will remain crucial for deeper understanding and social-emotional development, teachers can facilitate their lives by leveraging these powerful tools. LLMs are particularly effective at automating routine and repetitive language tasks, like those involving routine data entry, or roles such as credit authorizers, checkers, and clerks that may see a significant portion of their tasks automated through the use of intelligent systems where hardware and price is often the limiting factor. The rise of LLMs is also creating new job categories and opportunities. There will be a growing need for professionals to develop, fine-tune, and maintain LLMs, whether they be AI engineers, LLM developers, ML engineers, or others. Specialists who can effectively design prompts and end systems to optimize LLM performance. Experts ensure that LLMs produce ethical and unbiased content. While it may seem like many of our jobs can be augmented or automated, it doesn't mean AI will replace us. It simply means we can do better. A recent study compared a firm not adopting any AI versus another one adopting and fully using AI for commercial product orientation. They found that the first one will have a 6% probability of job loss in the next 3 years, while the AI first one will have an employment positive prospect increase to 16%. The rise of generative AI is transforming industries, nations, and individuals, presenting both vast opportunities and significant challenges. The key question is, how do we harness AI's potential while addressing its risks? Maximizing AI's benefits requires investments across the value chain, developing energy-efficient chips, advancing cloud infrastructure, and funding innovative AI applications. Governments and private sectors must collaborate, combining research incentive with policies that fuel innovation and competition. AI adoption will require major changes to the skill set that workers need, which is the goal of this course. From universities to online platforms, education must adapt to prepare an AI-enabled workforce. Blocking tools like ChatGPT isn't a solution. Embracing and integrating them is. Upskilling existing workers and rethinking how we teach future generations is essential. And, of course, policymakers and technologists must ensure fairness, transparency, and privacy while avoiding overly burdensome regulations that stifle innovation. The challenge lies in creating frameworks that balance responsible AI use with fostering competition across organizations of all sizes. In conclusion, the integration of LLMs into the workforce represents a transformative shift across industries, with significant potential to enhance productivity, creativity, and decision-making. Their current capabilities are particularly impactful in routine, repetitive, and information-intensive tasks, while human strength, such as creativity, critical thinking, and emotional intelligence remain indispensable. As LLM technology progresses, it will likely transition from assistive roles to more autonomous functions, making it essential for workers to adapt and learn to collaborate effectively with AI. The emergence of new roles in AI development, prompt engineering, and ethics highlights opportunities for growth in the AI-driven job landscape. To thrive in this evolving environment, individuals and organizations must prioritize reskilling and upskilling efforts, focusing on complementary human-AI workflows. The future of work is not about humans versus AI, but about forging a collaborative partnership that leverages the strength of both. Preparing for this shift will be key to unlock the full potential of LLMs in the years to come, and we are here to help you do that. LLMs aren't just for typing questions into a chatbot like ChatGPT or Claude. When they are combined with specialized tools and thoroughly designed interfaces, they become even more powerful for specific tasks and workflows. That's often where things get more interesting. For business leaders, this evolution translates into practical benefits like streamlining workflows, enhancing customer engagement, and enabling more effective, data-driven decision-making. Let's explore a concrete example providing real value thanks to LLMs, NotebookLM, a research assistant built by Google using its Gemini LLMs. Specifically, we'll show how NotebookLM helps with researching and understanding new topics. We'll break down its key features, show it in action, and then, most importantly, you will experiment with it yourself. NotebookLM isn't just another chatbot. It's a platform specifically built to help you research, synthesize information, and gain deeper insights into new topics. For instance, companies can use NotebookLM to conduct market research, perform competitive analysis, and quickly synthesize industry reports or research papers, all of which support strategic business decisions. This is also a great tool to introduce the audio capabilities of modern AI. Research performed with NotebookLM can be automatically transformed into a pretty nice audio podcast, or it can be used as the basis for a written report or educational tutorial or blog post you are working on.
Yeah, let's get into the specifics here. What are some of the common gamification elements that we actually see being used in online courses?
So this research you have, it includes a systematic review that identifies some key elements that pop up a lot.
Okay, I'm intrigued.
Indeed, both ChatGPT and Gemini now support native audio input and output, thanks to their multimodal models, and so does NotebookLM. And as you've heard, this isn't the clunky robotic voice synthesis anymore. It's much more fluid, faster to respond, and even allows interruptions. You can change the model's tone, speed, and emotion dynamically, making interactions feel more natural. That said, since audio mode is straightforward to test yourself, we won't spend too much time on explaining its uses in this course. Let's instead focus on how creators, like myself, can use NotebookLM to draft educational content and transform it into more engaging audio podcasts. But its applications go far beyond that. Beyond creating educational content, many organizations have applied similar generative AI tools to generate internal newsletters, streamline training programs, and enhance project reporting, all of which contribute to improved operational efficiency. Just sending a podcast version of your huge report can be a pretty cool preparation resource to an important meeting. But first, let's define what we mean by generative AI tools. A generative AI tool, sometimes referred to as an LLM wrapper, often use the same underlying models as AI chatbots like GPT-4o, for example, but with more structured pipelines built around them. Developers string together multiple prompts, retrieval augmented generation, or RAG, to add data to the model, and sometimes retrain or fine-tune adapted versions of the AI models to create more specialized applications. Some of these apps have grown into massive companies like Perplexity and Cursor, for example, which have each reached valuations near $10 billion. AI apps sometimes are built by the same labs that train the models, but many are developed by startups, solo developers, or even custom-built for internal company use. AI labs like OpenAI, Google DeepMind, and Anthropic often focus on developing cutting-edge models, improving scalability, and integrating multimodal and agentic capabilities. The generative tools that they develop typically serve as showcases for their underlying models. Startups, on the other hand, have to prioritize user experience, workflow optimization, and domain-specific applications. Companies like Jasper for AI writing, Runway for AI video editing, and Harvey for legal AI tailor LLMs to specialized industries. Startups frequently leverage APIs from major AI labs, but differentiate through unique interfaces, fine-tuned models, or proprietary data integrations. NotebookLM is a perfect showcase of the multimodal capabilities of the latest Gemini models from Google, especially for audio. The core idea is simple. You add sources about the topic you want to learn, then use the chat to gain insights and understanding, with Gemini always grounding its responses in your provided sources. You can create notebooks where you upload various types of content, documents, web pages, and even audio files, and then interact with Google's Gemini model through a chat interface. It's not just about summarizing text, it helps you analyze, compare, and synthesize information from multiple sources. NotebookLM is particularly useful for generating summaries, outlines, and study guides. It also provides answers with automatic inline citations, so you can be 100% sure that responses are grounded in your original material, so that hallucination problem of LLMs is already out. Now, let's get to the exciting part and try using NotebookLM to learn about e-learning gamification strategies. This demo will show what can be achieved with NotebookLM, so you can think of other applications relevant to your industry and personal workflows. Even before you start using the tool, you need to gather quality sources about the topic you want to learn. NotebookLM works best when you provide comprehensive and relevant source material, as with many LLM use cases where bringing your own high-quality sources can significantly improve output quality. To find the best sources for your learning, start by clearly defining your topic. Identify the specific aspect you want to teach, beginning with a broad perspective before narrowing your focus. Once you have a clear direction, search for relevant and credible sources using tools like Perplexity, ChatGPT with web browsing, or AI2 OpenScholar, as presented in the lesson research video. As you explore the topic, you may uncover new aspects worth investigating. Whenever you identify gaps in your understanding or notice that Gemini's responses lack depth in certain areas, add new sources to fill those gaps. After gathering your materials, take the time to understand them. While Gemini can assist in analyzing content, it's essential to read through your sources, even if only scanning the main points. Asking progressively deeper questions will help verify your understanding and ensure you have all the materials needed for your research. Finally, keep your sources well organized and easily accessible. This structure will allow you to track which areas of the topic are well covered and which require further research. The entire process is cyclical. Add sources, explore the material with Gemini, identify gaps, incorporate more sources, and continue refining your understanding until you are confident in your knowledge. Let's proceed to use NotebookLM and add our sources there. On the main page, you will see all your current notebooks. Click the Create New button to create a new notebook. You can think of a notebook as a collection of the content you want to work on, like a project container. We are now prompted to add information sources. We recommend finding these sources using a mix of the AI tools represented in the lesson research video, as we just mentioned. For our example topic, we upload 4 different research papers that explore different aspects of gamification in online learning. These papers discuss its effectiveness, current practices on learning platforms, its role in sustaining student engagement, and broader trends in e-learning. Once added, the sources will be displayed on the sidebar on the left. We are now ready to explore the features of NotebookLM. One of its key functionalities is automatically generating a summary of the uploaded sources. You can view a combined summary of all sources, access individual summaries by clicking each source, and ask specific questions in the chat to gain deeper insights into the material. NotebookLM can be a highly effective study companion, not only for summarizing materials, but also for creating quizzes and other study-related notes based on specific sources. However, while the tool offers valuable synthesized insights, you should carefully evaluate the quality and reliability of the generated information. AI-generated summaries, while efficient, may sometimes omit important details or overgeneralize key points. To ensure accuracy, it's essential to cross-check critical details directly with the original sources or verify insights by referencing multiple independent resources. If a summary lacks depth, asking more in-depth follow-up questions can encourage the AI to provide richer responses. Ultimately, the quality of the output depends on how thoughtful users engage with the tool. Applying your own expertise, critical thinking, and strategic questioning will make NotebookLM a powerful and reliable research assistant. One of NotebookLM's standout features, the one that put it on the map and made it viral, is its AI-generated podcast tool. It takes the research material and turns it into a simulated podcast with 2 hosts discussing the topic in a natural, engaging way.
We're starting with the basics. Force and motion.
Okay.
And that, of course, means we have to talk about Sir Isaac Newton and his 3 laws of motion.
Ah, yes, the foundation for understanding how objects move and interact.
It's not just robotic text-to-speech readout. It actually sounds like a conversation. It summarizes key points well, the voices are smooth and expressive, and the final product is surprisingly listenable. This is the prompt we provided to generate the podcast.
All right, so we're all about diving deep into some fascinating topics today. And, sometimes you just want to pick up some new knowledge, maybe for work, maybe just because you're curious.
Yeah, totally.
But who wants to get bogged down? You know, you want to learn things quickly but thoroughly.
Yeah.
And this whole idea of gamification, that's what we're looking at today.
It's a really cool concept, right? Making learning more engaging.
Exactly. It's like, how do we make learning fun and actually stick?
And that's where the games come in. And we've got a ton of material that looks at just that, how game elements are being used in online learning.
Especially in those MOOCs, those massive open online courses, they can be a bit of a challenge to stick with sometimes.
Totally. And your shared sources, they give us a really good overview of what's going on in this field.
So today we're going to break it down for you. What exactly is gamification in online learning and how is it actually being used in courses out there?
We're going to keep it nice and clear, give you some solid info without overloading you.
Yeah, we want you to walk away feeling like you've learned something new and interesting. So let's get started.
Sounds good.
Okay, so first things first, when we say gamification, what are we actually talking about here in the context of online learning?
Well, basically, it's taking those elements and principles from game design, what makes games so fun, and applying them to things that aren't games.
Okay, so like points and badges and leaderboard, stuff like that.
Exactly. Those are the kinds of things that are being integrated into online courses.
So we're not talking about turning like my history lecture into a full-blown video game.
No, not necessarily. Although there are some approaches that are more immersive than others. But the main goal here, as highlighted in the sources, it's all about boosting your motivation, getting you more actively involved in the learning and creating a more positive experience overall.
So making it more appealing and encouraging people to stick with it.
Absolutely. And that's where the whole structure of gamification comes in.
Okay.
Notice how the hosts have an interesting and engaging conversation about the uploaded content. We highly encourage experimenting with this podcasting feature to get an idea of its quality. It's honestly a fantastic way to get a good podcast-like recap of new reports or papers for me. In addition to using NotebookLM for creating a podcast, you can also try experimenting with it for your organizational use cases, such as turning detailed reports into short audio briefings, weekly audio summaries for market news or regulatory changes, transforming training manuals into an interactive audio conversation, and a lot more. Have fun playing with NotebookLM. Just make sure to always double-check what it says if you are to use it extensively or about to make an important decision. I hope you've enjoyed this short overview and demo of NotebookLM, and thank you for watching. Tackling a creative task like writing a blog or a training lesson about a technical topic like how do image generator models work can be daunting. Traditionally, this involves searching Google for academic papers and well-written blog posts, some Wikipedia sources, or even books, opening dozens of tabs, reading through redundant or irrelevant content, and extracting useful information manually. It's time-consuming and often frustrating. But there's a better way to approach research. Tools like Perplexity, ChatGPT Search, or AI2 OpenScholar, which integrates LLMs with real-time information retrieval. Today, I'll show you how to use them to make your research for any creative task faster, more accurate, and more efficient. Here, I'll focus on the concrete example of creating a course lesson like this one, but these tips apply to all similar writing tasks. As writers, we approached research by iteratively searching online, reading through articles, saving relevant information with links or sources, and repeating this process until we felt we had a good understanding and had fully covered the topic. While this works, it's quite inefficient. It takes a lot of time to read through irrelevant or duplicate content to identify the gems from the junk, or the needle in the haystack. Using LLMs out of the box for learning about a new topic is useful, but you must watch out for potential inaccurate information. It's generally good to use them to learn about popular topics that you don't know about. For example, they would be great for learning about a programming language like Python and write an article about it, as you are sure that the AI has been trained on a lot of great Python tutorials available in the web and can write about it confidently. On the other hand, if you want to write about the latest neural network paper from last week, in the best case, the LLM will say that it doesn't know about that topic. And in the worst case, it will invent information. In this case, it's better to provide the latest neural network paper to the LLM so that it can leverage its ability to write to answer your question. AI-powered tools like Perplexity, ChatGPT Search, and AI2 OpenScholar makes this easier by combining web search with LLMs. They retrieve the most relevant information from the web, summarize it, and even provide citations, making it easy to extract key insights without wading through unnecessary content while allowing you to verify its origin. Let's start with Perplexity. Perplexity connects LLMs with web searches, making it an ideal tool for efficient research. To start, type your main question into Perplexity, such as, how do image generator models work? Perplexity pulls information from trusted sources like research papers, technical blogs, and reputable websites, summarizing the important points. From here, you can refine your query to dive deeper into specific areas such as, what is the difference between autoregressive and diffusion models? Perplexity also provides a list of related questions based on your query. This feature is great for exploring your topic further and discovering new angles you did not think about before. To focus your research, use Perplexity's Focus Categories feature. For example, selecting academic ensures your results come from detailed, credible academic papers. Each response includes citations, allowing you to double-check sources and verify claims. Perplexity works great with many types of questions on different domains, and ChatGPT Search works very similarly. They are both optimized to write a great answer with very low latency, similar to how fast we expect search results to be presented when searching with Google. Instead, we also have AI2 OpenScholar that only focuses on research papers and on making sure to find all the relevant information to answer your question. This means that its answer can be more precise and comprehensive than those of Perplexity or ChatGPT, but at the expense of latency, as they can take more than 10 seconds to be produced. This is because the system spends more time on finding the best documents from the available ones. There are different ways to manage this trade-off of speed and quality, and we show them in our LLM developer course. These systems are still evolving rapidly nowadays, and we suggest that you try many of them to find what best suits your needs. As we said earlier, using an LLM without a web search tool can lead to hallucinations, plausible but false answers. LLMs rely on their training data, which might be outdated or incomplete. LLMs rarely tell you that they don't know the answer to a question. They were trained to provide an answer regardless of what they know, not to understand what they know and what they don't. Tools like Perplexity and AI2 OpenScholar mitigate this issue by using real-time retrieval to source answers from up-to-date external information. As we saw in our examples, these tools retrieved the latest papers and technical articles when researching autoregressive and diffusion models, ensuring we are working with credible information. Still, don't trust it blindly either. Always review the provided citations to validate the information and ensure your blog reflects current knowledge. Indeed, every time that an LLM is used to generate an answer, there's always a non-zero risk of inaccuracies and made-up information. Providing sources to the LLM just makes this much less likely. Different AI tools may manage this problem in different ways, always with a trade-off between latency and accuracy. Sometimes your research may involve understanding specific documents you've found online. In any case, it's always better to ensure a good understanding of what you refer to. If these documents contain non-sensitive data, many LLM platforms can help you extract important insights efficiently. Most major providers like ChatGPT, Perplexity, and Claude allow you to upload files such as PDFs directly into chat conversations. If you frequently refer to the same documents, these platforms also offer ways to store them for easy access. For example, you could create a custom GPT, set up a Perplexity space, or use a Claude project. This lets you start fresh conversations while keeping your important documents readily available. Once uploaded, you can ask questions to extract insights. This one, for example. If you are working with sensitive data, however, these platforms may not be a viable option. In such cases, you can consider building a custom Retrieval Augmented Generation or RAG pipeline, which we fully cover in the more advanced LLM developer course that we have. Here's how a typical RAG pipeline works. First, you split your documents into chunks and store them in a vector database. Second, you use APIs like Bing or Perplexity to gather relevant public information for your topic. Then, you merge private and public documents, ranking them by relevance to your query to ensure the most useful sources are prioritized. Finally, you feed the final set of documents into an LLM to produce a precise and comprehensive response tailored to your needs. For instance, if you are still working on that image generator technical explanation, you may take the documentation your team has on your approach and some recent online papers to give a complete review of the field and easily explain how your approach is unique. These systems are typically evaluated on two metrics: latency, which is how quickly relevant chunks are retrieved, and quality, or the accuracy and relevance of the information retrieved. If you are interested in building your own RAG pipeline, frameworks like Llama Index and LangChain are excellent starting points. These tools, available in TypeScript and Python, simplify the development process and help you learn the underlying concepts. To explore these techniques further with code, check out our complete course on building RAG systems for practical hands-on guidance. So using tools like Perplexity and custom RAG pipelines, you can streamline your research process, reduce inefficiencies, and create high-quality blogs or lessons. Real-time retrieval ensures your content is accurate and up-to-date, while citations help you verify and build trust. Whether researching public topics or private data, these tools offer a faster and smarter way to work. Happy researching and writing! Reasoning models, such as OpenAI's O1, can now act as powerful brainstorming assistants in a way better form than non-reasoning models ever could. These models enabled huge progress in AI capabilities and allowed LLMs to solve math, science, and code problems at levels comparable sometimes to doctorate-level experts, and some other times they are still below a junior level, which we always have to keep in mind. Still, when used the right way, they are incredibly powerful tools. Following reasoning models, we have to explore another significant step in AI development, AI agents. But before getting into that, it's worth taking a quick look at the bigger picture and what leading AI research companies are aiming for. Companies such as OpenAI, Anthropic, and Google are all explicitly pursuing some variant of what many term artificial general intelligence, or AGI. While AGI used to mean an AI that could handle any intellectual task a human could do, many AI company leaders have now narrowed the definition. Instead of focusing on general intelligence, they are aiming for AI that could perform economically valuable tasks, even if that means thousands of customized versions of a model working in different ways. OpenAI has a roadmap with 5 levels to track its progress toward its AGI goal. The first level is conversational AI, which includes models like those in ChatGPT or Claude and Gemini. These are the ones we are most familiar with, handling human-like dialogue. The second level is reasoning AI, which is where models like O1 come in, tackling more complex problem-solving, logical reasoning, and high-level expertise. The third level is autonomous AI, where things start getting really interesting. These agents don't just complete quick tasks. They handle longer multi-step processes with minimal supervision, adjusting as they go. This is what a lot of companies are aiming for these days, such as Devin, the AI software engineer developed by Cognition AI. The fourth level is innovating AI, which moves beyond solving problems to actually coming up with original ideas and insights. This is where models will start to extrapolate from their training data. We definitely have a lot to do to get there. And finally, at the top, there's organizational AI, capable of running entire companies, making strategic decisions, and managing complex operations. If or when that happens, it will change everything. In our course, we've already explored the first 2 levels, conversational AI and reasoning AI. As you've seen, a key enhancement to level 1 conversation is the tool use, expanding capabilities beyond the model's own by allowing it to send external requests to access external data or software. We taught some of this via features such as Perplexity, Code Interpreter, and NotebookLM. These tools already blur the line towards level 3 AI because they let models take some independent actions. But true autonomy, where AI isn't just a tool but more like a capable independent intern or even a contractor, is a whole different story. Instead of handling quick one-off tasks, level 3 AI can work on projects for minutes or even hours, making decisions and adapting as it goes. For AI to reach this level, it first needs solid reasoning skills. A good level 3 agent can't just randomly try things. It needs to plan, break down complex goals into steps, and make sure it's on the right track. That's why recent breakthroughs in reasoning models combined with advances in AI tool use over the past couple years have made level 3 AI much more achievable. In fact, a lot of people in top AI labs are calling 2025 the year of agents. Another key factor pushing this forward is the rapid improvement in multimodal AI. Agents can now process images, videos, and audio, which means they can actually see and understand digital environments more deeply than just under a text format. This is a game changer. An AI that can interpret a web page, recognize buttons, and navigate online is a huge step toward a real autonomy. And both OpenAI and Anthropic are on that mission with their computer use tools. Adopting LLM agents in your day job means learning to delegate sophisticated, time-consuming tasks like detailed market analysis, multi-source research, coding projects, or strategic data synthesis to AI. Rather than replacing professionals, agents amplify human capabilities, freeing your time and energy for more strategic, creative, and impactful work. For instance, a marketing manager could task an AI agent with gathering the latest customer feedback from various social media channels, summarizing key pain points, and even suggesting campaign IDs, turning hours of manual research into quick, automated workflows. Although these systems might sound technical, user-friendly interfaces and step-by-step instructions are making it easier for non-technical teams to incorporate AI agents into everyday workflows, without needing advanced coding skills. Now, before diving further in, let's take a look at what's really happening under the hood. AI chatbots that can use external tools are helpful, but real autonomy goes way beyond just answering questions. AI agents combine reasoning models with structured planning, memory, and tool use, allowing them to handle multi-step processes without needing constant human input. Instead of simply reacting to requests, they execute entire workflows from start to finish. Unlike a basic chatbot that just takes a question and spits out a response, an AI agent acts more like an orchestrator. It doesn't just process language. It plans out tasks, pulls in external data, analyzes information, and adjusts its strategy in real time. These agents continuously loop through a thought-action-observation cycle, using new information to refine their approach. You can think of a basic LLM as a one-shot thinker. It takes a problem, processes it, and spits out an answer. An LLM agent, on the other hand, knows when to stop, look for more information, run calculations, or reframe the problem before responding. It can recognize when it's missing key data and call on external resources to fill in the gaps. This makes them capable of handling complex and evolving queries. To get anything useful done, LLM agents rely on tools, external services or APIs that fetch information or execute specialized tasks. These can range from a search engine API pulling in real-time facts from the internet to a code interpreter crunching numbers with Python scripts it builds by itself, or a weather API, all with the goal of serving up live and reliable updates instead of hallucinating some. But having tools isn't enough. Agents need to know not just what they have at their disposal, but also when to use which. That means structuring requests properly and knowing when to stop guessing and start looking things up. A well-built agent won't just spit out nonsense when it's missing key facts. It will recognize the gap, fetch the missing information, and integrate it seamlessly. Planning is at the core of how all these agents operate. A good agent or agentic system breaks down complex requests into clear steps. If it recognizes it doesn't have enough data, it goes and finds it before answering the user. If a calculation is needed, it runs it. Every action is intentional, and this is where reasoning models play a huge role. To stay on track, advanced agents follow a continuous feedback loop: thought, action, and observation. First, the agent reflects on the user's request, what it already knows and what still needs to be figured out. It considers different strategies and decides what to do next. Then it takes action, maybe calling a tool, running a query, or even asking the user for more details. Once it gets results, it evaluates them. If something's off or something's missing, it adjusts its approach and continues refining until it reaches a solid conclusion. Another thing that sets these agents apart from simpler AI models is memory. Without memory, every interaction starts from scratch. But with it, an agent can accumulate knowledge throughout a session, making it capable of handling multi-step tasks more efficiently. Imagine asking an agent to find 3 reliable sources on innovative green energy products and then calculate their average reported growth rate. A basic model might just return a few links and try to do some sort of merged summary, leaving the rest to you. A memory-equipped complete agent will break the task down into steps, run searches, analyze sources, extract relevant data, store key insights, compute them with Python scripts, and keep track of its findings. If something is missing, it will go search for it. Once it has everything, it performs the final calculation, double-checks its work, and delivers a clear, well-organized response. This ability to retain and build on previous steps is what makes AI agents so powerful. Now, let's talk about some applied way we use agents. One of the earliest types of AI agents we saw are code agents. While software copilot tools are more popular at assisting developers as they work, coding agents instead aim to become autonomous software developers that can perform complex tasks in one go. A good example of this is the one I mentioned previously, Devin by Cognition Labs. Devin can code, debug, and iteratively solve software issues on its own. Well, that's when it doesn't completely fail at it. OpenAI is also working on a similar coding agent expected to automate large parts of software development. These types of agents are especially useful for teams without dedicated technical resources or few of them. However, feedback on Devin in practice has been quite mixed, and it has fallen behind the out-of-the-box capabilities of some reasoning models, such as Sonnet 3.7 with thinking mode, on some coding benchmarks when supervised well. In fact, to some degree, Sonnet 3.5 with its artifacts mode is blurring the lines towards more rudimentary code agents itself, as it can generate, fix, and render single-file projects in one go. ChatGPT with a code interpreter can also be thought of as a rudimentary coding agent, as it can perform multiple steps to analyze data using Python. However, these are both still largely single-task agents that work on short tasks and are best in collaboration and iteration with humans. They wouldn't be so good with complete large repositories, just like the recent Claude Code that isn't ideal. Perhaps most impactful for professional knowledge workers are web research agents. These specialized agents autonomously gather, analyze, and synthesize complex online data into structured reports, complete with citations. We will discuss these in great detail in our next video, showcasing powerful agents such as OpenAI's, Gemini's, Perplexity's, and xAI's deep research agents. These are a step beyond the Perplexity search tool we discussed previously. Then, there are general assistance agents, designed to handle all sorts of professional and everyday tasks. General assistant agents, like the recently viral Manus, handle diverse professional and everyday tasks. Manus can autonomously build custom websites, perform market analysis, or compare complex insurance policies and manage other real-world scenarios. This system integrates code execution, web browsing, multi-file code management, and interactive front-end generation. Manus especially stands out by combining all these functionalities into a single, streamlined system. Even though AI agents are becoming more powerful by the day, they still have a long way to go. Challenges like managing large amounts of context, handling vague or incomplete instructions, and maintaining accurate reasoning are still being worked on. They are still far from being conscious, whatever that really means. Researchers are focusing on improving memory systems, context management, and decision-making, all of which are necessary for building more advanced and reliable agents. At the same time, developers are bundling more tools and creating better virtual environments to give agents greater autonomy. What's cool is that the more LLMs progress, the better all our tools and those agents become. OpenAI has big plans for AI agents and is reportedly developing a line of specialized agents designed for high-value professional tasks. These will come in different pricing tiers, targeting different industries and expertise levels. According to reports, the pricing could range from $2,000 per month for knowledge workers like lawyers, consultants, and analysts, helping them with research and data analysis, to $10,000 per month for coding agent focused on software development and debugging. For even more advanced use cases, there are talks of $20,000 per month agents designed for PhD-level research, tackling complex tasks like hypothesis generation and scientific research. Reasoning models were a huge leap, but AI agents take things to another level, directly leveraging this reasoning leap. They don't just answer text questions, they complete complex tasks, adjust to new information, and manage workflows with increasing independence. While these agents are still in their early days, we expect big advancements as OpenAI and other competitors continue to push the limits of what's possible. This means it is worth spending time to upskill and stay up to date with these new technologies. In the next video, we will dive deeper into some of the most powerful AI agents currently available for business professionals, specifically web research agents, which are already proving to be a major productivity boost. LLMs like ChatGPT and Gemini handle lots of everyday tasks, summarizing documents, brainstorming ideas, answering customer queries, and much more. But these tools fall short when you need real depth, multi-step analysis, complex synthesis, and actual research. The solution? AI research agents. Hybrid that merge conversational AI with autonomous web browsing, tool integrations, multi-step reasoning, and multi-step actions. Yes, those already exist and they are real working and useful agents. Unlike chatbots, they don't just react. They think in a mechanical step-by-step way, not in a developing sentience way. They break down problems, gather data, and analyze it like a junior research assistant with unlimited energy, but perhaps still questionable judgment. These AI research agents, rather confusingly, have been branded the same name, Deep Research, across many leading AI players, whether it's OpenAI, xAI, Perplexity, or Gemini. A prominent example is OpenAI's Deep Search, built on its O3 model, which excels at tackling detailed research tasks. This isn't just a chatbot spitting out text. It actively investigates, often taking 5 to 30 minutes to pull together detailed citation-backed reports. That's a long time in AI terms, and it can cost a lot of money in token use, but the payoff is depth and reliability. Well, mostly. LLMs still hallucinate, and we'll get to that. Designed for professionals, these agents streamline workflows, whether it's conducting market analysis, reviewing literature, or synthesizing regulatory data, by providing comprehensive citation-backed results. So how can professionals like us make use of these agents? One of the biggest benefits of deep research tools is boost in professional productivity. It takes sprawling, complex, and manual research and boils it down into something clear, structured, and actually useful. For example, if we have a financial analyst trying to size up renewable energy startups before making an investment call, instead of drowning in Google search marathons, market reports, policy papers, and competitor data, they can offload the legwork to a deep research agent. In minutes, it compares a well-sourced, structured report outlining key financial metrics, market trends, and risk factors. What would normally take days of manual analysis served up in under an hour, and while you work on other tasks. You can simply confirm from the sources it gives you, and you'll have saved tons of hours of research and Googling. A marketing manager launching a new product can do something similar. Rather than cobbling together fragmented customer feedback, industry trends, and competitor strategies, they can have an AI agent sift through the noise, highlight emerging patterns, and deliver a concise, data-backed summary. That kind of speed means marketing teams can tweak messaging, adjust strategy, and capitalize on trends before the competition even notices them. Of course, like all LLMs, these AI agents are not infallible. Far from it. No matter how impressive these tools get, their insights still need human scrutiny. A deep research agent can accelerate the process, but it's your expertise that decides whether the conclusions hold water. Among these emerging agents, OpenAI's Deep Research clearly stands out. While OpenAI wasn't the first to launch a deep research agent, Google's Gemini Deep Research beat them to it, it's currently by far the best capable version we've tested. It also marks the first public exposure to OpenAI's O3 model, the most advanced LLM at the date of the recording. What sets Deep Research apart is its fine-tuned reinforcement learning. During training, the model was rewarded for finding accurate, relevant sources and completing research tasks effectively, making it uniquely customized for multi-step reasoning and structured investigation using web browser tools. Beyond pulling information from the web, Deep Research can also process documents, PDFs, and URLs provided by the user. This allows for deeper, more contextualized analysis, making it useful for professionals handling proprietary reports, regulatory filings, or academic papers. Deep Research is available to OpenAI's $200 per month pro users, who get 120 research tasks per month, not more, each one taking anywhere from 5 to 30 minutes, depending on complexity. and we have 10 of these queries for Plus and free tier users. So it's pretty limited unless you pay its price. But if you were to invest $200 monthly for an organizational productivity boost, here's how you would go about using it. The first step is to provide deep research with a task request. We generally find more detailed prompts to get the best results, where you communicate as much of your own expertise about the subject matter to direct the research. In our experiments, we found a few things extremely helpful. We recommend avoiding vague questions and clearly state what you need. Attaching relevant files or spreadsheets to guide the research helps with context. What also works is requesting a particular format, such as a report with sections or a comparison table. You can also find another LLM to brainstorm and optimize your prompt before submitting it to deep research. Remember, running a deep research is slow, limited, and expensive, so you want to optimize it beforehand. Also, this is much more iterative than chatbots, so be ready to answer clarification questions to refine the scope. It also means it takes time to generate outputs, so step away and wait for notifications. Finally, and we cannot stress this enough, verify results, as the tool may occasionally hallucinate facts or miss authoritative sources. Once the agent has been assigned the plan, it will request some clarifying details. Here, it tries to gather prompt details you may have forgotten to specify. It gets to work after you have replied with clarifications. It begins to search the web using OpenAI's Operator, a specialized web browsing system. Deep research goes through multiple sources, follows leads, refines its searches, and builds a logical thread of inquiry. It doesn't just skim the surface. It cross-references data, applies multi-reasoning steps, and even runs Python script for deeper analysis. If an interesting lead pops up, it adjusts its search dynamically, much like a diligent human researcher would. Unlike standard LLMs, which tend to work within a single query response cycle, deep research iterates, refining its investigation and re-evaluating its finding as it goes. In his typical exuberant style, OpenAI CEO Sam Altman said that my very approximate vibe is that it can do a single-digit percentage of all economically valuable tasks in the world, which is a wild milestone. While we wouldn't count on this just yet, we think this class of reasoning-powered agents is likely to progress LLM adoption and economic impact to the next level. That said, no AI is perfect, and neither is deep research. Like all LLMs, it hallucinates, misinterprets, and sometimes fabricates details. Its reliability also depends on the quality of its sources, so blind trust is never a good idea. But here's the key advantage. Even when verification is required, it's still significantly faster than researching from scratch. Deep research can surface critical insights in minutes, pulling together key facts that might have taken hours of manual browsing and link following. As long as you bring professional judgment to verify its outputs, it's an incredibly powerful tool. One that lets you focus on analysis and decision-making rather than on scrolling and clicking through endless links. That said, OpenAI isn't the only player in the AI research space. Other companies are building their own versions, each with strengths and weaknesses, depending on your needs. OpenAI currently performs the most in-depth research with full web browsing and the most customized reasoning models for this task. Google's Gemini Deep Research takes a slightly different approach. It lets you modify the research plan before execution, which gives you more control over the process. Its integration with Google Search and Knowledge Graph makes it excellent for general business research and competitive analysis. However, it tends to be weaker on deeper analytical reasoning compared to OpenAI's approach. It's fast, usually under 15 minutes, and cost-effective, but not always as thorough. Grok 3 Deep Search from xAI, available via the X platform, formerly Twitter, or via Grok, is designed for speed and real-time research. It's great for quickly understanding breaking news, industry trends, or fast-moving competitive landscapes. It also benefits from real-time information via X data. But a trade-off is depth. Grok is more like a high-speed news aggregator than a serious research agent. If you need quick insights, it's useful. If you need depth, it's limited. Perplexity Deep Research sits in the middle. It delivers well-structured, citation-backed summaries in just a few minutes. Great for exploratory research or quick fact-checking. However, it struggles with more complex, multi-step reasoning, making it less suited for deep analytical tasks compared to OpenAI's agent. It's a good balance between speed and depth, especially for professionals who need fast but reliable answers. Choosing the right AI research agent depends on the complexity of your task, your time constraint, and the level of depth you need. If you need thorough, well-structured analysis, OpenAI's deep research is the best option. If speed matters more than depth, Grok or Perplexity might be better choices. So, just to give you an idea of a broader landscape, we also tested out Grok 3 Deep Research. We asked it to gather examples of publicly shared real-world deep research chats in different industries to share in this lesson. The tool was quite quick and benefited from the access to X posts where we hoped some examples would have been shared. I put a link to the full Grok chat and response in the description of the video. The search was not entirely successful, but returned some useful examples. Here's just a small excerpt from it. Unfortunately, it only returned one direct link to a full public deep research report covering an example of using an agent for market research for product management shared in Peter Yang's Creator Economy newsletter. To wrap up, deep research agents aren't just better chatbots or hype agents. They represent a new way of integrating AI into professional workflows that we believe is there to stay. They shift AI from passive assistants to active research partners, helping professionals make smarter, faster, and better informed decisions while leveraging the inference compute scaling that's recently surfaced. Used thoroughly, these tools amplify expertise, not replace it. The best professionals will collaborate with AI, using it to handle tedious groundwork while focusing their energy on higher-level strategic thinking. However, you may want to create some new workflows around source verification if you want to use this research as the basis of formal reports. Just remember to always double-check generations and use them as a tool, not as replacement for human expertise. By now, you know how to craft precise prompts, which is primarily great communication. But doing it every time you need to get something done can get tiresome. Fortunately, just like expensive material, prompts can be recycled. If you're using an LLM regularly, you'll quickly notice that certain prompts become your go-to tools. Whether it's summarizing reports, drafting emails, or structuring data, reusing well-crafted prompts can save you an absurd amount of time. So let's talk about getting the LLMs to actually do what you want every time. By that, I mean making their outputs more robust and reliable. But there's just a small hiccup. LLMs aren't as predictable as a spreadsheet formula. And if you've seen the other videos, you know that I'm repeating myself. This is just because it's worth saying again. Just because a prompt works well on one task doesn't mean it's reliable across all variations of that task. Human professionals adjust instinctively when edge cases arise, but LLMs not so much. Don't get overconfident in their abilities to extrapolate. As we said in previous videos, they cannot do that very well. When working with chatbots like ChatGPT or Claude, simply writing a great initial prompt is rarely enough. Prompts yield variable responses even to exactly the same requests due to the inherent statistical fluctuations in LLM behavior. This variability isn't a flaw. Rather, it stems from how LLMs probabilistically interpret input and generate responses influenced by subtle internal parameters. One day, you might get a perfectly structured response, and the next, something completely off. And when models get updated or you switch to a different one, prompts that used to work might suddenly start producing unexpected results. Just like trying to use the same detailed step-by-step prompt you've been using with GPT-4o, but on O1 or O3, which are the reasoning models. While they may work, they are far from optimal due to how these new reasoning models were trained and behave. This constant model evolution is why you need a structured way to test, refine, and evaluate prompts, especially if you're using them on a larger scale. And that's exactly what we will cover today. The simplest way to improve a prompt is to experiment, try variations, and compare results. But you don't want to rely on gut instinct alone, or what we call vibe check. A more structured approach is extremely useful, especially for ongoing long-term projects. For example, A/B testing is a great way to compare prompts directly. Take two versions of a prompt, feed them to an LLM, and see which one performs better in terms of accuracy, clarity, and completeness. You can also run the same prompt through different models to figure out which one handles your task best. Since AI models update frequently, you also need to revisit critical prompts regularly. A prompt that worked last month might degrade after an update, so scheduling periodic reviews, say monthly, ensures your best prompts remain reliable. Likewise, if the response isn't ideal, you can simply edit the prompt you sent inside the chatbot UI and resend it until you get better responses to improve your prompt directly instead of continuing the discussion. And then, once you start recycling your prompts for repeatable tasks, a good enough prompt won't cut it. You'll always end up in the same loops with the model to finally get what you want. I've been there, and it's worth taking just a bit more time editing it so that you have a robust prompt. Such a robust prompt doesn't just ask for a result. It anticipates potential mistakes. It specifies things like output structure and other requirements like table headers, formats, and any hard or soft rules the model should follow. The goal is to reduce variability and make responses more predictable across different but similar tasks. But the truth is that even improved prompts can fail when encountering new edge cases. A small tweak might fix one issue while creating a new one elsewhere. That's why systemic testing is crucial compared to only vibe checking the results. Instead of making random adjustments, evaluate how a revised prompt performs across a range of realistic scenarios. Your industry expertise is key here. Identify tricky cases where the LLM might struggle and make sure your prompt holds up. Each iteration should solve a problem without creating new ones. Here's the not so fun part. Manually testing generated responses at scale can get exhausting fast. But guess what? You can use another LLM to do the heavy lifting for you here again. This method, called LLM as a judge, lets one model score another's outputs based on predefined criteria. For example, if you are using AI to draft client emails, you can ask a different model to evaluate the draft based on clarity, professionalism, accuracy, and completeness. For example, let's say we receive a client email draft from ChatGPT, then pass it to Claude. We could ask the model to check it with a prompt like this. Claude might then respond with scores and critiques like these. That's often more useful than just eyeballing it yourself. This feedback also guides a targeted prompt refinement to improve completeness and tone. However, this isn't foolproof. If both models share similar blind spots or biases, they might overlook the same errors or misjudge certain details. Their feedback can also shift when updated, so you can't rely entirely on them. A human reviewer is still crucial, especially where the stakes are high. Let LLMs lighten your workload, but don't leave them in charge blindly. Taking LLM as judge one step further, AI models aren't just useful for evaluations. They can also work together to refine outputs through iterative constructive feedback. Instead of relying on one as the final judge, you can have multiple models critique each other's outputs, creating a feedback loop that sharpens results. Just be sure to tell the model to be critical, otherwise it could give your output a glowing review just to please you. Cross-model feedback works because each LLM has its quirks. One might be detail-obsessed, another might excel at clarity, and a third could be a master of structure. And the best thing is that all these models have free tiers to use, and you can do all that without coding anything. Tossing work between them is like an AI-powered peer review system. Say you draft something with ChatGPT, Here, every revision isn't just about improving the output in the moment. It's also about learning lessons for refining your prompts for future tasks. The more you fine-tune and semi-automate your testing process, the more prompting turns into an ongoing cycle of improvement. This is a systematic way to navigate the complexities of prompt design, where each cycle of testing and refinement helps fine-tune the LLM's performance to better meet your application's needs and make it more robust to use in new scenarios. Another best practice is keeping a version history of your prompts. That way, if a new version performs worse, you can quickly roll back. Document what prompts worked, what outputs were, and why you made each change. Over time, this archive becomes an invaluable cheat sheet for designing effective prompts. Once you've fine-tuned your prompts through trial, error, and a fair bit of cursing at uncooperative LLM responses, the next challenge is making them consistently reliable across an entire organization. Fortunately, you don't need to spend your days copying these manually. Tools like ChatGPT's custom GPTs or Gemini's gems allow you to lock in your best prompts, ensuring your whole team benefits from your hard-earned prompting expertise. Custom GPTs act as personalized versions of ChatGPT tailored to your company's workflows, brand voice, or proprietary datasets, no coding required. Instead of feeding the model the same instructions every time or repeatedly uploading reference materials, you can bake these elements into a reusable system. Many chatbots also allow creation of projects to more easily organize your prompts and in some cases to share them. Just a heads up, you will need a ChatGPT paid subscription to create custom GPTs. Take Moderna, for example. Since early 2023, they rolled out ChatGPT Enterprise across thousands of employees, building an internal library of specialized GPTs tailored for everything from regulatory compliance to translating complex biotech jargon into investor-friendly language. Their Dose ID GPT, for instance, helps clinical teams analyze data for dosing decisions by referencing proprietary datasets, generating well-cited visualizations, and supporting expert judgment. The impact? In just 2 months, Moderna created 750 custom GPTs with 30% of weekly active users contributing their own. On average, each employee engages in about 120 ChatGPT Enterprise conversations per week. Their structured approach, rigorous testing, AI-driven prompt evaluation, and careful iteration ensures that even as usage scales, quality and accuracy remain intact. Instead of AI becoming a quirky experiment stuck in one department, it's embedded across the company as a serious productivity multiplier. Now, let's put all of this into practice ourselves and consider this scenario. We have Jessica, a financial analyst at an investment advisory firm, who spends her time summarizing quarterly earnings calls. Her managers want precision, clear financial guidance, and explicitly stated strategic risks. Let's see how she iterates on her prompts using the actual Q4 2024 earnings call from NVIDIA. Of course, she supplies the full transcript to the This simple example highlights the importance of careful prompt phrasing when you don't know exactly what information the model has access to. This mistake may have been very difficult and time-consuming to check for and to identify manually, which we still encourage you to do if you can, or at least the same way Jessica did. With the feedback that net income guidance simply doesn't exist, Jessica zeroes in on rephrasing to ensure she doesn't request too specific details that may not exist. And this time, no hallucinations and just a really valuable answer. Instead of fabricating net income figures, the model sticks to actual guidance, revenue projections, margin commentary, a clear growth driver, and an explicit risk from the call. But Jessica isn't done yet. If she wants a generalizable prompt that works across all of the 30 companies she looks at each quarter, she will need to stress test it much further. What happens if a company skips guidance altogether? Will the model invent numbers again? She will likely also bring in more of the prompt techniques we taught already, such as few-shot prompting or chain of thought, with more directions based on what she evaluates over all the 30 companies. The good news is she doesn't have to manually test all of this. LLM as a judge allow her to scale evaluation, ensuring that over time she develops a rock-solid prompt. She also logs every iteration, so when earnings season rolls around again, she isn't starting from scratch. Unfortunately, real-world examples get much more complex than this study case. But the same process applies where it's much more valuable to clearly evaluate your prompts and results in a quantitative way to leverage LLMs properly. Prompt design isn't something you figure out once and forget about, especially if you are planning to use AI on a larger scale. It requires a structured, systematic approach and improvement over time through continuous testing, refinement, and evaluation. The coolest part is that AI itself can even help with this process, acting as an evaluator to speed up iteration and spot mistakes that wouldn't have been very hard to find yourself. I hope this video helped you understand a way you can experiment with LLMs in your day-to-day workflows or give you some ideas on how to approach prompting in your next project. Thank you for watching, and I'll see you in the next one.